the food area. So when we're around today, anything that we serve will be on the right-hand side. I'm going to just make note that there is some food out in the little hallway out here. That is for a different meeting. So please don't take the other meeting's food. We just want to make sure that we are respectful to them as well. And their table happens to be out in the hallway. So our table is in here. And I ask that you, let me reshare this here. I ask that you enjoy the food here in this room. The next thing is parking. I guess everyone found their way there. If anyone has any questions about parking, please let me know. There's a Wi-Fi login paper on every single table, so please join the Bosch network and accept the terms of service, and we can get you going there. Password is on the table and on the screen right now. And then the last thing is the schedule. So today's schedule's packed with 5 amazing speakers before lunch. And then we'll break for lunch, and in the afternoon, we are going to go into the working group meetings, similar to how we did yesterday. We will have the benchmarks working group in here, the software portability working group across the hallway where it was. We'll escort you over and show you where that is if you need any assistance. And then cybersecurity is overflow. We did conclude that yesterday, so unless we announce anything different, the cybersecurity working group will not be happening this afternoon. And then finally this afternoon, we'll gather back here just to say goodbye and close out the conference. So thank you for that. I'm thrilled to announce our second day keynote. So Jyotika Athavale has joined us from IEEE and Synopsys. I've heard nothing but amazing things about her, so I was so glad to finally meet her in person this morning. And she's going to be talking about addressing automotive functional safety, the challenges that are there with silicon lifecycle management. So I'd love to welcome Jyotika to the stage. Just takes a quick second. Sorry, everybody. I just have to go and share for the online people. So. Lost my mouse again. Okay. Sorry. Wait. Get you going. And if anything's wrong with the folks online, I'm going to go fix it. But apologies, it took a second. Thanks.
Not at all. Thank you so much, Sarah, and hi everyone. And it's really an honor to be here today. And I'd like to express my gratitude to all of the organizers, AVCC for the invitation. I'd like to thank Bosch for hosting this. It's a great facility. So I'm Jyotika Athavale, based in Sunnyvale, California, and work at Synopsys. It's my day job. I'm also a volunteer with IEEE, and this year serving as the president of the Computer Society. I just flew in this morning from California, and so a little bit jet lagged, but I'm always happy to be here in the Midwest, and it gives me that warm, fuzzy feeling because this is where I went to college, and so it brings back memories of when I was way younger, and went to school here. But there's something to be said about the Midwestern hospitality. So always have that feeling when I'm here. The topic I wanted to talk about today was about functional safety challenges with silicon lifecycle management. But also, I just wanted to briefly share my perspective from the Computer Society. Having served this year, leading the charge across the geos, across the globe, various different technologies, various activities and program boards that we drive in the Computer Society, standards, conferences, publications, educational activities, as well as member and geographic activities. So I just wanted to mention that this is a really important area for IEEE and for the Computer Society as a whole. There's a lot of investment in terms of resources and effort driving various different activities across our program boards. Each year, the Computer Society also comes together. We have a committee called Future Directions, and we pull in experts from academia, industry, and government all across the globe to put together a technology predictions report. And that is to forecast which are the key technologies that will be successful in a given year in terms of maturity, as well as in terms of impact to humanity, because that is our mission with IEEE. But I wanted to share that the autonomous technology, as well as functional safety and reliability, scored very well on our ranking. And they were ranked between 10 and 11 on the list of technologies for 2024. So if you get a chance, I'd encourage you to download the Technology Predictions Report from the Computer Society website. It's free, and it's really informative and gives a good perspective to the work that we do today. Outside of that, I also chair a standards committee in the computers in IEEE. It's the IEEE P2851 on functional safety interoperability. And it's a committee that we kicked off early 2020, and last year we published our first standard on functional safety data format for interoperability within the dependability life cycle. But of course, automotive is one of the key domains that is applicable to the scope of that standard, in addition to other safety critical domains like industrial robotics, medical, and avionics. So we do have a lot of active standardization initiatives coming out of the Functional Safety Standards Committee within the IEEE Standards Association as well. So that was just a little bit to share my perspective from the Computer Society and IEEE, given my engagement there. Now I'll talk about what we're doing in Synopsys to address this, with the work in silicon lifecycle management and what that is all about. All right, so this is just to set the stage. So nothing new here. I think everyone here is familiar with the challenges that we are seeing today in automotive with respect to silicon requirements, and the growing complexity in both hardware and software. So increasing scale, increasing system complexity, which is posing challenges from a reliability and thereby safety standpoint as well. So technology scaling, going to smaller geometries from a process technology standpoint, integrating more on chip, on the system, more memory, more logic, growing complexity even in the software stack. And all of that introduces new vulnerabilities and new risks for reliability, for security, as well as for safety. As we move, from FinFET to gate-all-around process technology nodes now 3 nanometer and beyond, we are again seeing those challenges with both the intrinsic wear-out failure mechanisms as well as extrinsic, which is the manufacturing defect-induced failures. And so that's something that is of concern. We'll talk about it a little bit as we go through these slides. But more risks of shorts, more risks in which the things can go wrong and errors can cause failures in the field. So that's with the advanced node adoption, new safety requirements, so extended lifetime, ASIL-D, low failure rates, low DPM, low outgoing quality DPM. And then the zonal architectures with higher compute, pushing performance more aggressively. And this is challenging, as we know, we have a backed up curve, and we're getting hit from both sides, with the infant mortality related failures increasing because of our increasing susceptibility to those extrinsic manufacturing defect-induced failures. And then on the right side, with the exponential increase in the wear-out, shifting left because now we're pushing performance and we're seeing the intrinsic wear-out happening faster. So getting squeezed from both sides. And I was sharing this at one of the conferences, and they said, well, the bathtub curve is no longer a bathtub; it's more like a standing shower now. Because you're getting pushed from both the sides, and you can't even have a bath. But anyway, a little bit more about the landscape, right? So we talked about the scale complexity, the design size, smaller geometries, transistor density, higher manufacturing variability. The other thing is the packaging evolution. So new form factors, multi-die, chiplet-based architectures, 3D ICs, and these introduce new failure modes, new failure mechanisms that we need to address. Proactively shifting left and looking at what we can do in our design and architecture to mitigate those with diagnostics upfront, during the development cycle, but then also the need to continue to monitor the health of these parts in the field such that we are detecting any anomalies in the field and taking proactive action. System complexity, we talked about this, the aging degradation aspects, dealing with large volumes of data, and so security becomes an issue, and then unpredictable workloads, workload consolidation, the challenge of having a representative workload to do all of our D&B work during the safety engineering life cycle, such that it's representative of the applications, the varied applications that we would see in the field during normal operations. So all of that is the challenge. And then I'll talk about where silicon lifecycle management comes in, or what it is even, because it's kind of it's still a relatively new term used in the industry since the last few years. We'll talk about what it means at each phase of the life cycle, meaning what does it mean during design, during manufacturing, during production, and then during in the field. So my background is in device physics, so I'll be talking more about those aspects of reliability from a process technology standpoint. But here's kind of the technology trend that we're seeing. This is for Intel, process technology node, and I spent 2 decades of my career working at Intel in the technology manufacturing group. So seeing the evolution from planar to FinFET and now to GAA. But this is kind of showing, the transition from Intel 10 to 4 to 18 angstroms, and as we move from FinFET to gate all around, the greater susceptibility is seen in the middle of line, or the MOL, as well as the back end of line. So we have the 3 levels, the FEOL, MEOL, and BEOL. The FEOL is the transistor reliability, the BEOL is the interconnect or the back-end reliability, and the MOL is that middle region, which is the contact region between the transistor and interconnect, which is the most vulnerable region, and that's where we're seeing, we're seeing more of those defect types associated with the MOL and these new process technology nodes, and that's kind of the focus with respect to driving more data collection, driving more stress experiments, more DOEs to collect and characterize our reliability models, and understand how these are manifesting, what are the kinds of defects that are causing the failures that we are seeing on our new technologies. So long story short, fabrication failure rates on 7 nanometer and below are rising. The difference is on planar. So for example, a couple of decades ago, for anyone of you that worked on planar process technology nodes, we were concerned about intrinsic wear out, we were concerned about gate oxide TDDB, device degradation, like, device temperature instability, hot carrier degradation, those kinds of mechanisms. Today, that's not gone away. However, what you're seeing in the Pareto and those defect rates, we are seeing more of a dominance of the defects that are from external causes, or what we call extrinsic defects. And that is because, with the technology scaling, we are now seeing those manufacturing defect-induced failures. We see a relative increase in those kinds of failures. And so that becomes a concern because, the kinds of testing that we do at time zero, the screening that we do is not sufficient, and we have to be able to catch these failures up front before we see them proliferate into the field. So we have to get better at testing, we have to get better at our monitoring techniques in the field to be able to catch any walking wounded parts that were not caught, during the testing, and have now made their way into normal operation. So that's one of the key areas of focus, what we call the extrinsic defects. That could be latent at time zero or not present at time zero, and then start to get symptomatic, as parts are shipped into the field. So that's one of the causes of the circuit functionalities and anomalies that we see in the field. The other one that's not gone away is, this is on GAA, is the time-dependent dielectric breakdown, or gate oxide TDDB, and the hot carrier instability. So as you can see here, comparison between 4, 5, and 6 nanometer, that we are seeing that increase. So we did see an improvement on FinFET when we went from planar to FinFET, but now moving to GAA, we're seeing the worsening again of these intrinsic wear mechanisms. So it's kind of that double whammy, both from the intrinsic wear out side as well as the extrinsic defects side, that we are seeing now, a growing risk from a reliability standpoint on our new process technology nodes. So here's that shifting right that I was mentioning earlier in the backtop curve. The red line that you see here shows that increased infant mortality or early life failures due to more of those defects that are not detected or caught during our screening, and we're seeing more and more of this on our sub 20 nanometer process technology nodes. But it doesn't stop there. So you see that also bleed into the useful life of the part. We would expect to see a constant failure rate, but now you're seeing, those failures are not stopping just during the IM phase, but moving into the useful life of the part, which is not what we would want to see. So the reason I bring this up is, this is the reason why it becomes more important for us to have those prognostics capabilities in the field to be able to detect the degradation for these, what we call degrading faults, which were either due to intermittent faults, so they were not caught, because with an intermittent fault, you need a certain specific combination of temperature, voltage, and frequency to activate that fault, or it was a latent fault which was not symptomatic at time zero and then started to get symptomatic only later in the field, or the fault was not present at time zero and is now starting to progress in the field. So monitoring some critical parameters such as timing, Riemann, or frequency in the field are indicators that can be used to understand the progression of that fault. When it crosses a predefined threshold, then it can trigger warning or corrective action that needs to be taken by the user. The other thing is calculation of the remaining useful life. So, as we are continuing to push performance and squeeze out, all of the performance that we can from our parts, we are starting to see the degradation happening earlier, even on the right side of the bathtub curve. And so being able to calculate the useful life that is remaining at a given point in time, at a given during normal operation, and being able to take the necessary corrective action to be able to extend that useful life out, such as swapping out a core or a lane, changing the voltage, using throttle or cooling solutions, redirecting the workload or the traffic. So whatever that corrective action may be, so as to balance the degradation across the chip and extend the useful life. All right, so what else is happening? So we talked about the silicon, but we're also seeing new use cases, new operating profiles. The traditional automotive use case of 10 years, 15% on time is no longer valid. You're seeing new use cases of always on, 130,000 hours, which is again, very comparable to the server use case, and so pushing us, both from a performance and reliability standpoint, and just emphasizes the need to be able to make those trade-off decisions, the optimizations that we need to make to be able to get the adequate reliability performance, safety performance from our products. All right, so we all know that mission profiles change dramatically between design and in-field. When we talk about mission profile, we're talking about the assumptions that go into our reliability models based on a given use case, right? So what is the expected voltage, duration, time and state, temperature of the part in the field. And when I was doing reliability modeling at Intel, we always made assumptions that were really, really conservative because we wanted to bake in that additional margin in our products. But measuring these same parameters in the field gives you, a lot more accuracy, and you're able to fine-tune your models. So that data is really helpful in making those optimization decisions between reliability and performance. And that's, I'll talk about how the SLM plays in here with respect to the PPT sensors that we have which are able to measure these parameters in field. But it's not just the delta from design to in-field. You also see that variability across the fleet. And so, being able to have access to that data, the fleet level data, to be able to do the analysis and calculations and gather those valuable insights based on that mission profile, for example, for a 100-car fleet, and then use that data to also detect outliers and take corrective action as needed. So that's one of the other value propositions of SLM. So here we will talk about what SLM is. SLM is a solution that is used to monitor, collect, analyze, and act. So what we mean by that is when you talk about monitors, we're talking about IP sensors. These are embedded in the chip early in the design phase. And then that data from these monitors and sensors, so these are monitors and sensors like ring oscillators, path margin monitors, PVT sensors, or clock and delay monitors, activity monitors. And so these monitors are used during mission mode to measure, critical parameters that are representative of the degradation that you expect to see, in the logic paths, in the memory arrays during normal operation. And that data is then collected, via a framework on chip. It's analyzed and useful insights can be gathered from that data. So you can take the necessary action as needed during these different phases, so during design, during manufacturing, during production and in-field. And there's different value propositions for each one of those phases, as we'll talk about. But another key challenge that is today plaguing the hyperscaler industry is this SDC problem, which is silent data corruption, not due to the traditional causes, which was radiation-induced or transient faults. Now we're talking about SDC for other causes, such as the manufacturing defects that we talked about, such as the intermittent faults or degrading faults. And there again, SLM can be valuable, using the insights from the data that we collect during these different phases to predict an SDC error before it occurs, reduce the downtime, and reduce a catastrophic event from happening. So here's the SLM solution. It talks about the different on-chip monitors which are embedded in the SoC. We have the test infrastructure as well as the software that is used for the analytics. And the data that the infrastructure that we have, we also work closely with the OCP or the Open Compute Project community. So working to make sure that the framework that we develop is compliant with them. The analytics that we provide, such as remaining useful life or mission profile, or functional safety metrics, such as the diagnostic coverage improvement due to SLM, treating it as a safety mechanism. All of these insights can be gathered and used as metrics to compare with the requirements for a given safety integrity level for that system, for a given use case. And then, we can drive corrective action as needed. So on the right, you see some examples of those, the RUL. There's also a lot of work happening in the standardization community today about, discussing different methodologies to calculate RUL and to do that prediction. We have within the Computer Society, within the Functional Safety Standards Committee, we had a study group that published a white paper just earlier this year on prognostics and talked about the flow chart and methodologies for predicting RUL, for calculating the mission profile. The committee that I'm chairing now, the B2851.1, is looking at functional safety, interoperability with reliability. And so one of those key topics there is prognostics and predictive maintenance, also covering the use cases that we have listed here. ISO 26262 third edition is going to include guidance based on the TR9839 hardware predictive maintenance report that they published last year. So across the standardization landscape as well, there's a lot of work happening on these topics. So here's a little bit more about the SLM components, the solution components. We have the IP. As listed here, the environmental monitors, such as the process voltage temperature monitor, droop detector. We have the structural monitors like the path margin monitors and the XL best. Functional monitors like clock and delay monitors, which measure the clock to Q delays for memory cells. We have the data transport IP, such as the HSAT, high-speed access and test. And then there's other optimized implementation as well. There's software and analytics. We have during manufacturing silicon.da as well as the monitor analytics. We also leverage the valuable insights based on AI. So we are using AI in our run prediction in the field to have that inference based on pre-trained models using stress test data from HDOL and other stresses that are done during qual to be able to infer in the field. And then other in-field analytics, we have monitor drivers, SLM firmware for the necessary data collection and telemetry, as well as the SLM virtualization tools. And so here's what we call the SLM highway. So it goes all the way from on-chip, the subsystem, the system, and all the way through the cloud. So we have, the solution is end-to-end. So, you're seeing the on-chip data, which is collected with sensors and monitors. Sorry. So we have the data collected by the on-chip monitors and sensors, then being fed into the controllers through the fabric on-chip, through the server that we have on-chip, and then it goes to a processing unit, which is the SLM, the SPU that we call the SLM processing unit, to do the necessary pre-processing, filtering, storage of the data based on, what criteria do we need to apply. Now that we have all of this data that we are collecting from these monitors, how do we understand what is good data versus anomalous data, and then use that and feed that to a data collection framework in software that is then fed up the stack. And so this framework works both ways, so feeding the data up to the cloud, and then also using that failure information down to do diagnosis back to the chip. So it's both ways. It works for prognosis as well as for diagnosis. And so it's that end-to-end capability. We talked about these, so I'm going to skip the slide, but these are the buckets in which we categorize our SLM IP, the environmental, structural, and functional IP. And then here's more information on those categories as well. We have high-speed access and test, close compute to improve serviceability. We have the UCIe, monitor, test, and repair solution, logic-based, star memory system, which includes our star ECC, IP. We have, and then on the right side, you're seeing all of our monitors and sensors, such as the EMM, CDM, BBT, SHS, which are used for logic as well as memory across the chip. Now, one of the things I wanted to point out is, of course, these monitors cannot be used across 100% of the die. So we do also provide a flow, since Synopsys is an EDA company, and so that's one of our strengths is the tools and flows. So we leverage that to provide guidance on where these monitors can be strategically placed across the chip using various criteria, such as looking at speed paths, high activity paths, looking at the temperature gradient across the chip, looking at vulnerability factor analysis, and then using all of those criteria to narrow down on which are the locations where these sensors and monitors should be placed to be able to detect where the failures are expected to happen early. So besides the aging and reliability that we've been discussing, up to this point, SLM is also used for power performance optimization. So the insights that we get with these monitors can be used for use cases related to power performance optimization as well, and as well as for predictive maintenance, as we talked about, which is especially critical for use cases in automotive, where we need that early remediation to prevent mass recalls and prevent catastrophic events happening in the field. Later on in this deck, I'll talk about also one of the first IEEE standards that was written on predictive maintenance, the IEEE 1856, which introduced the metrics for predictive maintenance, and then later that was referenced in the ISO TR 9839 report, which is now being integrated into ISO 26262. That PAR is now again active. They're continuing the work. There's an 1856.1, which is working on implementation aspects of that. The reason I bring up the standards is because we are ensuring in the work that we're doing in SLM is that we are complying with that guidance, with those requirements and the methodologies that are being discussed within those industry committees as best known methods, as best practices. So these are the four phases for SLM, as we talked about, in design, in ramp, and manufacturing and production, and then in field. And each phase has its own value proposition, such as optimization, the citizen comparison to improve optimization between performance, power, reliability, metrics, during manufacturing, improving yield, right? So yield optimization and margin correlation, and then in field, improving aging, reliability, as well as safety. Via those use cases that we talked about in mission profile, RUL, improving diagnostic coverage by treating SLM as a diagnostic, and then also the adaptive voltage scaling. So typically, in the past, we used to design in an Fmax guard band, looking at our worst case speed paths and then designing in that additional margin, but we can no longer afford to do that because we are pushing performance so much. And so ABS is really the technique where we can dynamically adjust that guard band in the field based on the data that we collect, and we don't have to over-design and compromise on performance. Okay, so this one talks a little bit also about the diagnosis part, which we discussed. So, if there is a timing failure, path margin monitors can help us root cause to the location of that failing path. Thermal sensors can tell us about the change in thermal gradient, where the hotspots are on the chip, and the voltage monitors can indicate any significant voltage droop. We do know that in case of reliability, even instantaneous spikes can cause, sudden or catastrophic damage. And so these kinds of monitors that are looking at those instantaneous spikes are really important. It's not just used for modeling for long-term reliability, but also for those instantaneous events. And then the in-field analytics, I think we covered that quite a bit. Here's kind of a summary of all of the useful insights that are applicable, from an automotive use case standpoint, which is the increased or enhanced serviceability, feature enhancements, increased safety and trust, low cost of predictive maintenance, brand loyalty and revenues, and then prognosis and diagnosis. So all in all, looking at it holistically from an automotive use case standpoint. So we'll dive into, one of my favorite topics now, which is functional safety, where I spend most of my cycles during my day job. But here we're talking about what's happening now in ISO 26262 3rd edition, and also how we are aligning with that in our B2851 standardization work. So in the ISO 26262 2nd edition, we had, in terms of terminology, we had permanent faults, intermittent faults, and transient faults. And now, we are looking at degrading faults and understanding the life cycle of a degrading fault and how it can be useful in designing a prognostic solution. And we're also looking at the link between these degrading faults and the extrinsic defects that we are seeing on these new process technology nodes. The implication of this is not just improving our time zero DPM, which is our ongoing quality DPM, but also looking at how we can improve our end-of-life DPM, which is our reliability DPM, and also our safety metrics. So here's that standard I was referring to, the IEEE 1856, which was written in 2017 by the IEEE Reliability Society, was the first standard on prognostics, and introduced these three metrics on response time, prognostic distance, and prognostic system accuracy, where response time is the time between the detection of the fault and the first correct prediction of RUL, and then you have the prognostic distance, the time between the correct prediction and the actual occurrence of the failure, and then the accuracy of that prediction. And that's shown here, again, on the chart on the left. You can see on the time scale those three key metrics as introduced by that standard. On the right is the chart there is from the ISO report, the technical report, the TR-9039, showing the life cycle of a degrading fault. The solid line is the life cycle of the curve is for a healthy part and shows the Wieman degradation for a healthy part. The dashed line is in the presence of a fault, and you can see that Wieman degradation shifting left. And then when it crosses a certain threshold is when the failure will occur. So this work is also now being integrated into the ISO 26262. How does this help us for safety? So the improvement is in our metrics for both SPFM as well as for PMHS. SPFM, the single point fault metric for ASIL D, we need to be greater than 99%. This is our overall diagnostic coverage of the chip. So treating the SLM or prognostics capability as a safety mechanism, we get that boost in our diagnostic coverage, and we're able to apply that additional prognosis coverage towards the total SPFM. Increase in the PMHF, which is the probabilistic metric for random hardware failures, that's the residual bit rate, and that is improved because now we have more accurate mission profile, and so less conservatism baked into our reliability model, which is useful for calculating our base failure rate that feeds into our safety analysis and produces that residual failure rate. So both ways we get an improvement in our metrics, which helps us to get to a higher ASIL as well. Here's an example of the remaining useful life prediction, and as I was mentioning, this shows an example in the presence of AI. So using that baseline data from stress testing like PHDOL to train the RUL model, and then deploying that model in the field, and then doing inference on that based on measured data with our SLM monitors, and using that to predict the RUL. And down there you can see that in the context of the degrading fault life cycle curve that we saw in the ISO technical report. So here's just an example of how you can use, or the algorithm that you can use to predict RUL with the prognostics capability. So to summarize, and I think I'm getting close to the end of the talk, the in-field SLM benefits for automotive are improved quality and reliability. So for time zero DPM, improved reliability and in-field or end-of-life DPM, and then improved availability, so reduced downtime. Improved power performance optimization, and then improved serviceability, predictive maintenance, and functional safety. And so we saw examples of each of those. So in summary, we are seeing a growing challenge of addressing RAS, reliability, availability, serviceability, which is necessitating the need for increased resiliency of our hardware components. So we need to move higher up. We need to shift left and address this in our silicon, in our design and architecture. But that's not free. it comes at a price tag, and we have to optimize. It's not possible to protect every single element on the chip, and therefore it becomes critical to be able to have our eyes on the chip in the field, to be able to monitor these vulnerable elements on chip and being able to infer these insights based on the data that we collect in the field. And that's what we are trying to do with SLM and silicon lifecycle management, and compliance to these RAS solutions will help us to improve product resilience and also address sudden data corruption. Thank you very much, and I'm happy to take any questions.
So the question I have is, as we start looking at chiplets and the ability to go cross node, how do you perceive that in the SLM relevant to the, do you anticipate an increase in failure mechanisms that are, let's say, intrinsic to the connection methodology because of that scaling factor, or do you think you're going to have greater stability based on the node maturity rather than having mixed nodes?
Yeah, it's a great question. Thanks for asking. So my understanding is the move to chiplets was from monolithic to chiplet was primarily to improve yield, right, for yield improvement. But it did introduce new failure mechanisms now. So, with the UCIe, the automotive UCIe, we do have one of our SLM solutions that is looking at UCIe testing repair, also monitoring signal integrity. Looking at that, we have a signal integrity monitor at the SIM. We're looking at bit error rates. So there are, every time we change these architectures, we do introduce new failure mechanisms, and we have to make sure that we are addressing those, monitoring those. As we go into multi-die, also 3DRC, we have to consider thermal issues there with respect to self-heating, and how do we mitigate those, and how do we monitor those in the field. So for sure, I think, we try to fix something, but then, we have to make sure we have checks and balances for the, the implications of those changes. And so I think the same holds as we talked about moving from FinFET to GA, but yeah, I don't know if I answered your question, but that's
Thank you.
Thanks.
So you talked about the concept of remaining useful life and the first correct prediction. How do you know that the prediction is correct?
So you don't, right? And that is why with every value that you predict, you have to have a confidence level. You have to have that level of uncertainty that you need to define. And so there is a methodology for that as well that we describe in our white paper, AVCC white paper, as to how to look at false positives, how do you define that uncertainty and the confidence level associated with the prediction. Because it'll never be a point value, it'll be that range.
Nice talk, Jyotika. Just a question from SLM point of view. What I understand is that it is coming from, you can say, SoC manufacturers towards tier 1 and the OEM. Now, how do we have the traceability of what has happened during the manufacturing that is being utilized by the tier 1 OEMs to say that, okay, what is the good life of the product and how we can really go into, let's say, adaptability of the performance so that the vehicle is not impacted.
That's right. Yeah, so I think it's really important that we have that end-to-end solution, right? And so, going all the way from the SoC to the system, looking at, to the application layer and looking at the data that is being transported across our SLM highway. I was sharing on one of the slides. So it's to look at that, how that data is, or how that fault would manifest as an error or propagate into a failure. And so that's kind of the prognosis part of things where you're trying to predict events in the future, and then the diagnosis part, which is where, you're looking at maybe a failure that happened, and then root causing it to diagnosing it to the location of that fault back on the chip. So having that end-to-end view is important, but also I think that working together as a community to be able to share the data across those boundaries, between the chip vendor, the tier one, the OEM, so that we can have that traceability across those levels and across those boundaries. Thank you.
Once you mentioned about the chip aging, and then once you detect that there is some fault or some chip aging, how do you recover from that on feed?
So it's a great question. There's different types of corrective actions that one can take. So for example, you can swap out a core, right? So if you find an issue in a core, you can redirect the workload to a different path. You can swap out a lane. You can employ throttle or even cooling solution. So there's different kinds of dial up and down the voltage. So different ways in which you can try to recover from that, or use those medications to extend your lifetime. If where that what is getting overheated, or here's where I'm seeing that this is my timing path where I'm seeing more of my margin being utilized. So how can I fix that? So once you know that you have a problem, you can design your corrective action accordingly. But in the absence of that, you're basically running blind.
You do that, you have to have like extra margin built in your system, or you start shutting off functions, right?
You may have to, but you may not either. So for example, say I'm running an application and I have 6 cores, and I'm just using one of my cores. That's being utilized, and that gets like 100% aged. I can now redirect that application, utilize one of my other cores that are not being just sitting idle and not being utilized. Or I may redirect the traffic to another portion of my my chip that is not being utilized. So you don't necessarily have to build in that margin, because you're not leveraging all of your chip evenly, right? So if you redistribute your application to other resources on chip that are not being leveraged, is one way. But the other one is also, like as I was mentioning, the adaptive voltage scaling, or the ADAS, right? You don't necessarily have to design in all that extra guard band up front, but you can dynamically adjust it in the field based on the data that you're collecting.
So who typically does the monitoring? Is that by the OEM or the tier or the chip supplier?
So these are some of the monitors that are embedded on chip, and then so it's all frameware, like so it's end to end. So then the data is collected from those monitors, which to controllers through the fabric to the SNM processing unit on chip, is fed to the data collector in the software, and then fed off the cloud to the application layer. So it's a complete end-to-end solution, and all of the stakeholders across the value chain play a part and have to be involved in the sharing of that data and enabling all of the necessary plumbing, so to speak, and that have that end-to-end framework. So as I was mentioning, OCP, or Open Compute Project, is working on RAS API and hardware fault management framework and methodology. So we are working to be compliant with that in our solution. Did that answer your question?
I just wonder if the tools available, like for OEM, or is that something that the chip suppliers have to?
So it has to be, the monitors have to be designed on the chip, right? So which is going to be part of the system that the OEM is going to be using. So if it's not, if the monitors are not integrated in the chip, then they're not going to be able to use or leverage those insights.
Okay.
The back end.
So, if you had sort of only partial connectivity, let's say that, you know, you didn't have the back end to the cloud, how much of the corrective action can you take based on just the SLM unit on the chip itself? Right, like you mentioned ABS, but are there other things that can be done?
Yes, even RUL, right?
Okay.
So you can define your RUL domains on the chip. Maybe it's by IP or maybe it's component level. And so you can, you know, make those predictions at the SoC level as well. Mission profile, you know, that information can also be gathered at the chip level. ADAS, the adaptable to scaling at the chip level as well. So pretty much, I think you can define the level at which, but however, I think if you go higher up, the insights are more valuable in my view, just because a lot of it is looking at outliers. And, you know, getting that fleet level view is very important to be able to understand the outliers rather than just looking at a single unit.
I think we're running low on time, but a question came in online, actually multiple questions have come in, so I don't want to ignore the online audience. I want to make sure they get theirs in. If we could ask one question from online, and then we're going to need to close the question and answer session down. Jyotika will be around. I encourage you to have additional conversations, and if something comes up that you think the whole attendee audience, AVCC audience would benefit from, we can do a webinar, we can do a blog post, so your question will be answered. The question from online is, what information data points needs to be fed to the cloud for prognostic purpose for in-field monitoring of SoCs?
Yeah, so it's a good question. It depends on what sensors and monitors you have designed into your chip. So for example, if you have your path margin monitors, clock and delay monitors, then you're pulling the timing delays of the TCQ data, the timing data from those monitors. If it's PVT monitors, then you have the process voltage temperature data that you're collecting. You may have signal integrity monitors, and then you have data there on the signal integrity. So you could have data from all of these monitors, or if you just design in a subset of those, then you're just putting in those parameters that you are collecting via the monitors that you have included in your mission.
And is there a standard or document available to reference that?
Yes, a lot of documents are online as well on our website. If you go to the Synopsys SLM page, there's documentation on all of the available sensors, monitors, test solutions for our SLM hiring.
Excellent. All right. Well, thank you so much.
Thanks very much.
I think Jyotika is going to be a popular person right after this presentation, so I encourage you to catch up with her. Okay, we're going to take a quick break. I'm going to load Stan's presentation, and we'll be back in just a minute. Thanks. All right, so send who an email. I'm not on this. No, I can't get it here. You send it to, hey, Steven, can you help?
Sure.
So his PowerPoint, he wants to use the one from an email.
Yeah, I need to use my laptop.
So.
Actually, it's my email.
Is it still on here?
I'm Tim.
With that.
Yeah, when you first, when we first brought, yeah. First.
So we have a variety of different sets of English. We just have
We'll see the Miller.
Now, I will say, you will see those technologies are on by the why they are actually design to them already, and then once it's in production, once it's in garbage, okay, that's again now. We want to change the field.
You know what?
Right. But also
I think all industry has something else we don't because like the OEM come back to the and then we take time and bring it up and then check this. Yeah, we coordinate everybody to make sure it's working. It might be simple, right? And then we spend days and then we tell back to the system, oh, it's your problem. No, it's your problem, right?
that's right. So having end-to-end is about the diagnosis. I think the problem is
Sometimes it's a thing like, MFA, you're like, MFA, they try to association. It's almost. So what I'm saying. Yes, yeah. So basically, yeah, go to something. So it's like. Yes, yes, money.
Yeah. You can have some people who want to stop and stuff.
Yeah, wondering whether.
Yeah.
Some working. Okay.
Yeah, so I'm making sure we can use, so that people will enjoy our something. Basically, on the we're focusing more on Q&R and we have all the Right.
I
was
curious about that.
That was the one.
That's what I was asking about the connectivity.
Yeah.
The thing is, though, that last thing you described, then you send all your sensor information to the cloud.
Yeah.
The cloud will get the judgments on our calculator. I was wondering what the Friday. In a different way to talk.
Yeah. But, yeah, I think it's in touch with our culture,
Injection.
Yeah, that's right.
And I'm not prepared. We can equalize it. I don't know if they are. Yeah, sure. That's why.
I appreciate that. I need to go back and look at the bylaws and just take a look.
I think you can.
I'm sorry. All right, we are back. So if everybody will find their seat. All right, thank you for your patience. I appreciate that. I would love to introduce Stan Schneider. Stan is the CEO of RTI, and he's been active in the AVCC for years. I remember when we met. So I appreciate his contribution. Today, he's going to be talking about autonomy is like happiness, and we look forward to hearing what he has to say in the contribution. Thanks, Stan.
Sorry, I was delayed there. Technical this stuff.
What's with the head off?
I'd like to start out with a big picture, timeline. Big pictures. Where's your timeline start? Big bang. Big picture. Let's start with timeline of technology, what happened. So, Earth came along 4 billion years ago, like shortly thereafter, first single cell life. Then animals and dinosaurs and humans.
What scale is this on?
Civilization.
What scale is this on?
You'll figure out the scale. Something I could do with the resolution. And then the Tamagotchi. And then Star Trek in about 300 years, Foundation, Asimov's great stuff. Earth ends, and then that's the universe. Somewhere in there. So you might go, well, which one doesn't seem normal? Tamagotchi here, you might think a little bit out of place, but I don't think it's out of place at all, any more than life is the first single-celled animal. This is the first single-celled portable computer that, acts like life. I think it's important to think that. And, you are here on that thin red line. If it was drawn to scale, that line would be a couple atoms thick. Very hard to do that. You wouldn't be able to see it. But in that little line, there's a dawn of science, computers, smart things, autonomy, and a smart planet. All fits in that line, less than 1,000 years. And we live there. If you think about it, that's amazing. What a special moment. We're at a profound transition moment. That thin red line that goes from natural intelligence developing over billions of years into sort of an artificial intelligence age that I like to call that physically defined world, and we're in the software defined world. And I know it's AI, but I think it's software enables AI. It's a more general term to be software defined. I just wanted to start out with some perspective. I put this together a little while ago. There's a bunch of chip people in here. How much will computers improve? I'm not going to argue what that word means. In 40 years, this is a Moore's law, something like that. Anybody guess what that is? No calculators? Quickly, about 100 million. That's a lot. At first, that can't be true. I went back. This is my first portable computer. Yeah. Anybody have an HP 41C? My friends all have a TI. What do you got? 441 bytes. It cost $300. Way back then, when I put this together, I had an LG V30. It's got 32 gigabytes. Well, 100 million times 441 is actually a little bit. Right about 32 gigabytes. 3.12 is the inflation factor between these 40 years. It's actually a little cheaper than 100 million. So, what are you going to do? Take that forward another 100 million. 2060, everything that you have in an Amazon or Google high-end data center, you can have 4 of those. You can carry it around. It'll be less than $1,000 in today's dollars. I don't have. If you think about that, it's incredible. I mean, hats off to all the chip people in the room. You've made the software relevant. Because that's, sort of my view. The historians are going to look back at our time and wonder how we got by without smart things. Smart cars, smart medical systems, smart airplanes, smart everything. And it's not a question of if, the only question is when, and it's going to be before 2060. It's not that far out. What's becoming smart software defined? Well, we have RTI works in lots of different areas. Medicine is already building AI into things like patient monitoring imaging systems. You guys know about vehicles. You call it a cylindrical vehicle architecture. a hardware definition of the software concepts. Defense, going to what that is, but all the industry will be software defined now, all that long from now. It's really pretty amazing. And, why is it better? Well, wiring harness is the third heaviest and third most expensive thing in the car. And you can make it all easy with, lightweight communications backbone, you get rid of a lot of ECUs and it's less expensive. That's what people say. I think this is a very minor benefit. It's just reducing the hardware cost a little bit. The big deal, software-defined vehicles move functionality to hardware to software. That's as profound as anything I've said here today. It's becoming software-defined. It really changes everything. I wish, or Stephen, you had a question. I wish you'd asked how long will be before the value in software is worth more than the value of all the hardware in the car, including the windshield wipers. That would have been an interesting thing. I don't think it's very far from now. Software is really getting there. Software is also very expensive, but we'll leave that. But what can you do with software? Well, it really lets you do everything. You get features, you can evolve things over the air. The OEMs can keep in touch with their customers. Big deal. Changing all their business models. You manage fleets. You can reduce liability. How do you reduce liability? Because you can do updates, right? You can fault tolerance. You actually can reduce the certification cost. You may notice that China doesn't certify anything. Why do they not certify anything? Because they're almost 100% software defined and they're almost 100% over the air updates. And they do care about safety. I had some survey data in here. I took it out of it. They're in iterative safety. There's two paths to software quality. You can test the snot out of it. That's called the 26262. 26262 is how many dollars it costs you to do a new line of software. Not really. Or you can iterate. And iterate is much 99% of the software in the world quality increases through iteration. They put out new versions. They put out new versions quickly. There is safety issues, of course, with that. Don't get me wrong. We support all the safety certifications as well, but it's way faster and it's way. It will eventually win if it's quick. You can also do other things like teleoperation. You can patch things with vulnerability. You can build ecosystems and autonomy. So I'm going to give you a little background. I couldn't come to Michigan and talk and not put up this slide. I'm from Michigan. I grew up in Grand Rapids. 2 degrees at the University of Michigan. I worked while I was there at it wasn't called this back then, but UMTRI, University of Michigan Transportation Research Institute, crashing cars for a living, parts of cars. This is our sled. I ran the sled a bazillion times. This is actually a test of I think it's a 12-year-old child dummy. This is a demonstration of why your kid needs a booster seat. You do not want to restrain your child by its neck. Crash, not a good plan. Anyhow, I learned a lot from that. One thing I learned is I don't believe human drivers are ever going to be a good safety system. Getting there is dangerous, and no offense to anybody in the room, but you're not a good safety system. You're not a good safety system. Autonomous cars 1.0, when they're really out there, I'll talk about that in a second, will be a safer driver than all of you, and 2.0 might be as good as I am. Anyhow, I think we have a moral obligation to automate driving. I just don't think we're going to stop that. Back when I was in Michigan, 45,000 people a year were dying on the highways. Anybody know what was last year?
Probably close to 40,000.
Yeah, 43,000. It went down for a little bit and then back up. No, we're driving a lot more miles. Per mile, it's much better, but we haven't fixed the number one safety problem. I don't think that's going to be easy to do with people. So the problem is fully autonomous, truly autonomous. How many people have been asked how long it's going to be till we have autonomous cars? I don't think there's an answer to that question. Truly autonomous isn't. Autonomous is like happiness. Raise your hand if you're fully happy. It just, you know, they can always improve. They're noble pursuits. They depend on the environment. You can be fully happy at home and not so happy at work. Very different. They have to evolve over time. You need some external help. I believe the way you the traffic problem I had back there is some teleoperation or some higher intelligence. Best definition of autonomy, by the way, is the length of time before you need help from a higher intelligence or another intelligence. Everybody here, nobody here is autonomous either. Right? I need my wife's help all the time just to get the dishes done. Both are noble pursuits. I don't think we're going to be, you know, fully or perfectly autonomous. I do think we have to build an architecture that can evolve, proving to get somewhere. And I think a real challenge here is you can't do it alone. You can be in an organization like this. You can do it alone if you're Google for a while. You get that much money, you can do it. You can just give up on autonomy. That's another option. Or you can get to an organization where people are trying to get together. Anyhow, this is the problem with autonomy. Tried to find a picture of corner cases. That's the best I could find. You know, it's really hard. And it's really hard for lots of reasons. The real world is hard. It's gonna take a long time to do it. You have to have an ecosystem. Everybody talks about the tier ones and the hardware supply chain in Western economies is really well developed. So OEMs, and tier ones, and tier twos, tier threes, and us. Joe, you got it. Okay. Anyhow, you have to have a business model where that works. You have to have a data architecture. I'm going to talk about that in a second. You have to have some way to know how to get information out there. And then, you know, we really need an architecture to enable an evolving ecosystem. That's really sort of where we are. I'm back up for a second, sort of, you know, where we are today in AI. So everybody knows what AI is. Smart systems mean both AI and distributed sharing. AI today is everywhere. Really not, except for autonomous vehicles. AIs run in the cloud. And most of them, until recently, were just modeling people so they could figure out what ads to throw at you. Today, you know, ChatGPT and things do a lot more, but the key to intelligence, everybody knows, no surprise, is data. But AI in the cloud have days, weeks, months, years, decades to figure out how to process that data. If you want to do something in the real world, you got to get the right data, the right place, the right time, because you're going to have milliseconds, not seconds, maybe even fractions of milliseconds to figure out where the pedestrian, to figure out where the other vehicles on the road are. And it's really hard. It's harder than you think because it's mobile. As soon as you get mobile, connectivity becomes a problem. Power becomes a problem. Reliability becomes a problem. These systems can be huge. Software system, if you can't really just think of the vehicle, you have to think of the vehicle system and cloud and all the connections to operators and things like that. Security is a problem. It can be globally distributed. Latency can be a huge problem. So that thing. But the real big problem is code complexity. It's very complicated, very fast. The systems we work with almost all cost over $100 million, if not multiple billions of dollars. Building an autonomous car, it's a multi-billion-dollar commitment. They can take years or decades, and then once you're out in the field, it takes another decades or more. They have to exist, and that really is the problem out there. So I believe that we need new perspective. What do you guys think of this picture? Does it look right? Look a little bit weird?
Yeah.
Anybody know what's wrong with it? Usually a room this size, someone will figure out what's wrong with it.
AI generated.
What?
It's AI generated.
No, it's not AI generated. It's upside down. The reflection in the lake. I put this here because that's sort of the way I think most people think of data architectures. If you think of system components, the chips, the servers, the networks, and then figure out later what data is going to flow over them and go somewhere. It's very different when you think about what data you have and where it has to go and when, and then design a system that can handle it. And this is much more flexible. And once you've seen this lake the right way, it'll never look right this way again. And I like that as an analogy because I think that's really what we're talking about here. Data centricity, which you've talked about a little bit, trying to give you a little bit higher level view. Fundamentally, data-centric systems talk to the data. In reality, it's virtual, they're talking directly application, but as far as you know, you're talking to the data. Databases, a database is storage, data at rest, but it collects data and then you can get it later. Query it, you can get it later. A data bus, which Rajiv talked about, sends information through the data. So I'll explain what that means. There's no messages, there's no clients, there's no servers, there's no remote objects. It may be publish, subscribe, it may be service oriented, but all of these things are completely subservient to the fact that you're only talking to the data. And then you'll see drawings like this, where you put this up, or instead of talking about figuring out how to interface between all the different applications, which is quite the mess in a large system. You draw this way. It's sort of a convenient thing. I don't like this. What this means is these applications are only talking to the data. It's not like a wiring diagram where running wires down the bus, talking to the data. I suppose it is sort of like a bus architecture. Then you can add these things and everything's clean. So a data architecture is really important. There's 3 parts. Every system, every computing system has to have, they have to know what you're going to share. We'll call it data model. Database people call it data table, or type, schema, something like that. You have to have an interface, an API that you can actually figure out how to get to it. And then you have to have some idea of what the paradigm is. And there's really, if you have these things figured out, if you don't have any of these things, you're not going to have any interoperability, let alone any ability to build a big system. If you have them figured out and well defined, then you can do lots of great stuff with it. So software interfacing is fundamentally harder than hardware interfacing. I think very good. I think this is the reason the OEMs, the automotive industry is struggling with software, because they just don't understand that you have to have all 3 of these things to make it work. And I don't hear much conversation about those things out there, except places like here. So data centricity makes it even simpler. I like to think of it as a virtual memory model, taking all the data in the system. And this could be, all the LiDARs and radars in your car. It could also be the 100,000 cars on the road. Don't underestimate that orange box. That's everything you need to execute. And what we're going to do is we're going to make it look like it's in your own local memory, your local operating system, your own formats, byte ordering, whatever. You write in Python, it looks like it's Python memory, whatever. But you can get the right data, the goal is get the right data at the right place at the right time. We know ahead of time what applications need to have. That's sort of the hook. And then we're going to go and put the data in there so it looks like it's virtually there, because we know what time it has to be there too. And this happens to work really well for things like high bandwidth area flows like AIs. So this is what the applications sort of look like. All of them have some kind of algorithms. You can write the algorithms, just reading and writing its own memory of data. Virtually everybody has some kind of sensoring. You write those, reading and writing data. You're going to have actuators, and almost all the systems we work with have some kind of operator offline help or online help elsewhere, where you can monitor what the systems are doing. And all these things work like that. The way a control system works is we know the sensor is producing data. We put that data in the algorithm memory just before it runs. We actually trigger it to run. That's a detail. And then we stick in the actuator before the loop closes. And with this little system, you can close the control loop. And it's actually sending the data directly. So there's no hops or anything like that. And of course, we're doing that with all the data in the system background. That was only 2 flows. We have some systems with over 10 million flows. It's phenomenally complicated in large systems. Beyond modeling, you sort of have to really understand this. And anyway, why does it make mobility easier? Well, if your data looks like it's virtual, you can move those things. It doesn't matter if you move an algorithm to the cloud or it's moving around the road. It's mobile. Makes software integration easier because you can have these layers of data where everybody's got the data they need to run. It makes scalability easier because you can build layers of buses here that sort of connect things together with a different data model. A bus like this, by the way, implies a single type of data model. So it's same kind of information is flowing on there. All the applications can discover what that is and use it to produce it. It makes feedback. And by the way, I tried to find a picture of a car without a steering wheel. It's not that easy to find, and it still has rear view mirrors. Right, and what good are rear view mirrors on the steering wheel and brakes? That's sort of an interesting, scary thought. But anyhow, precision feedback's easier because we can take the sensors, directly connect to the algorithm, directly connect to the motors. We control that. We have systems running closed loop feedback loops in multiple kilohertz. I mean, it's, you know, far less than a millisecond. But then there's always other things that are slower going on out there. There's situation analysis and localization, and maybe using the same sensor sets. There's complex things like planning that are also feeding into the system at different rates, and you got to be able to control all those rates. Data centricity is pretty smart about knowing, well, this thing's going to update every 10th of a second. That thing needs to operate every 500 times a second. It'll make that work. By balancing the buses. We'll talk about that in a second. Security actually has a very big advantage here because we know what data is going where. One of the parameters of data, because you have to have the right certificate, and it won't deliver it to you unless you do, and it can be directional. So sensors can only write. Algorithms can only read that data and write that data. It really, if this gets the sensor, for instance, gets corrupted and you know it, you're not going to be able to, if this gets corrupted, you can't get into the sensor. It just makes the whole system simpler. You can also have read but not write, so you can monitor but not be able to write data. Very difficult to do with all the other kind of network technologies out there. It does have, you want to be local, you want to be fast. Sometimes you also want to be geographically distributed. You can solve that with a discovery service. It actually tells you how to hook up, so you're not actually sending anything through the whole cloud connection if you don't need to. Many times that's not important. It also makes evolution easier. Everybody knows this evolution process here, but this allows you to build more complex software systems as you go. How does that actually work? Well, today you have all these ECUs. You can put some little gateways in there, and you sort of miss the subtlety that a lot of these algorithms moved out to the gateways. You put in central CPU and move even more. You can put in the cloud and add functionality in the cloud. All these things can move around because as long as you satisfy your performance specifications for each of the pieces of software, that software can move. It's not as simple as that, obviously. It does make a difference. It also makes platforms easier. You don't have to worry about language or operating system or chip architecture you're on. It can actually do the translation. It knows what you have and what you're sending, so that makes a big difference. The data flow coordination is actually pretty nice. There's lots of different kinds and speeds and volumes of sensing. And if the bus knows about all those things and knows what needs to go where, it can actually do all that for you. So you can put all these things on a single bus, a single flow. It really makes these things easier. And then if you have these little magic things that we call routing services, translate between the buses, you can integrate lots of very complex technologies that may not have been designed together. It's actually pretty useful. So some things might connect directly to your bus and other things have to be translated, but as long as you meet all of your quality service specifications, that can be done. Anyhow, I'm into software because that's what we do. I'll give you a quick view. Advertising about RTI is a software company. We've been connecting AI algorithms to like functional AI, which is getting more and more towards real AI, whatever that means. Distributed devices for a while. We actually started out in the autonomous vehicle space with flying things. We have experience with over 250 autonomous vehicle designs. None of them are fully autonomous. Most of them are fully autonomous, depending on how you want to define that. We do have quite a bit going on in the road vehicles, mostly with the software-defined vehicles from day one, which are EV new entrants. But we have flying things, underwater things, surface vehicles, delivery robots, forklifts, lots of agriculture, construction and mining machines, all those kind of things. We have some experience with making that work in the right environment. It's doable. We also work in the medical space. Defense sort of picked up the DDS standard 15 years ago now, I suppose. It's we're running almost all the U.S. Navy ships, almost all the anti-air defense. Lots of things like that have to be distributed fast. Some of the bigger things like big operation centers like Canada's air traffic control and NASA's launch control system. All these things, you can build these large complex software systems. And then we run the Western Grid power balancing system and lots of wind turbines, things like that. So, give you an idea. We're 300 employees, big in this industry. Software companies aren't as big as hardware companies doing this kind of stuff. We do have a product that does this. We support all, even though I blast. I think the future of certification is going to change in software. We do support certification now for sure. We have our own AI as well. Pretty interesting. Anybody have an AI they're actually selling or working with in their company? It is really an interesting journey. Let's just put it that way. We took chat AI. It doesn't even matter what the base AI is, and we have all this data. We're running about over $1 trillion worth of stuff, but all of our documentation and training and use cases that were shareable, and then spent months and months and months on making it not make stuff up. It can be done. It's just not easy. It's in a narrow area. And it's great. It's free. You can go to our website and download it and play with it. It's amazing what you can ask it about what kind of systems, what the data models would look like for an autonomous car that does this kind of thing, or a LiDAR system or something. A reasonable job of helping. If it works in Japanese or Spanish. So I thought I'd end with, why are we in the AVCC? I think we sort of need a marketplace enabler. It's focused a lot on chips now. We're the software, trying to drive the software side. I think there's a hole in the industry and consortia out there. There's really nobody building production quality, not research quality. Talk with somebody here about open source here. But something that you can actually put into vehicles in the short term here, both for processor capabilities, how fast processors have to be, all the benchmarking work, but also software architecture. I just don't think there's another consortium out there doing that. And fundamentally, what it's going to do is, what we're trying to do is help build a data model here that will change the market perception and a market competitive basis from ECU components really to software interfaces. That's a big key change, and this is the key enablers coming up with that data architecture for that to work. We have our first paper out there, TR005, and inspiring way better than TR004. I mean, whatever number standards and things should be shot. I'm sorry, but whatever. Actually, the speaker yesterday did a better job with this. But why this is the Gartner hype cycle curve? I very much believe in this curve. I put a picture of winter here because, in the peak of inflation, everybody can do it. Everybody can have autonomous cars. Ford isn't supposed to have any steering wheels by now, right? I promise, no more of them. Anybody can do it. At the bottom, well, nobody can do it. And somewhere here, somebody did it. That's really the way that works. If you really look at it here, everybody thinks it's impossible. Someone put impossible for autonomy on the thing yesterday. Well, somebody has to work really hard. And then winter turns into spring. And it just works and nobody knows why. And what really happened is somebody worked hard and the reason to be an AVCC is to be somebody. It's hard work to do this. So I want to welcome you to the real world, AI in the real world. You live in the thin red line. It's truly an amazing point in global universe history. And I think there's a future here, a very different way of doing transportation. Very hard to find a good picture of that, but I think intelligence changes everything. It really will make everything is going to be smart. Everything is going to be distributed. That's something people don't really understand. They don't think about it as much. The networking and pervasive networking is just as changing and profound as processor speeds. Also, I think everything's going to be data centric because I just don't. Once you've seen the lake upside right side up, it's really hard to think of a world where you're not figuring out where the data flows first and then figuring out how to build it. So connect with me on LinkedIn. That's me. That's it. Question?
Spoke about timelines, Stan, in your presentation. At what point in the development of a vehicle, the timeline of developing a vehicle, does it help to start thinking, having that data-centric approach? Is it when SoCs are being developed, when ECUs are being developed? Is it when you're looking at the whole system, when the architecture of the vehicle?
You lost me when you said the vehicle. It's really not the vehicle. It's like saying, you know, when you're developing a computer, when do you first start talking whether it's going to have a processor in it? The whole evolutionary timeline builds computers. I think the industry, the software definition to me is very different feeling. It's not something you can easily evolve to. You've got to really think of it. Software design is the vehicle.
So as companies developing SoCs, right, should we be thinking about that?
Should definitely be thinking about it now. Yes. I think, well, I mean, there's a transition period going on right now, and absolutely you need to, so that the TCO work that I think Elizabeth started is really important. It really bothers me that I can have a phone that I will never use all the memory of. I've never probably used the whole processor of. It didn't cost me that much really, but a vehicle, every single chip in there is optimized to have only less and such memory, and that really just precludes the idea that you're going to be developing software over time. So definitely think you need to think about it, the software design and the software evolution path while you're designing the memory size, if nothing else. You know, until the mindset changes to stop trying to optimize every little penny out of cost of the hardware, and instead thinks about how to optimize the cost of software. It's going to be hard to answer that question. It's really an industry evolutionary change. You definitely see some companies that have absolutely bought into that. And divisions of companies that are split off from the main line. Many more sort of, even the traditional OEMs are thinking that way now. You guys are more into the hardware side than I am. But we definitely don't see the kind of pressure we had to use 270 bytes. 262 would do.
Well, thank you,
I
Stan.
don't think that's a good question.
I'll dismiss everybody. All right, thank you. Thank you so much, Stan. And Stan made special arrangements to be here and he wasn't planning on it. And then we asked him to come and present. So I really appreciate him rearranging his schedule in this afternoon to to be here with us, or this morning to be here with us. So we're gonna take a quick coffee break for everyone online. We're gonna shift our timeline. Please be back at 11 a.m. Eastern. So 15-minute coffee break. We do have refreshments over on the right-hand side of the room and beverages on the left. Please do not take the food out of the hallway. So thanks so much. We'll see you in about 15 minutes.
So how do, so it's like down below, the problem is that I don't see the house.
Stay small, please. You know, John Elvin? Long time ago. We did a lot of it. Yeah, it was a great play. Yeah, so. Yeah.
When we come back, we'll
Get
just
back
open
there.
and then just get presentation.
Yeah, if they don't have.
Yeah, let's go.
They always just.
Yeah.
All right, we are back. So it is my pleasure to welcome Neil Banerjee to the stage. So Neil, I met Neil more recently than a lot of the other people and the other speakers that we've had. So Neil was a former executive with Fisker, and he has joined AVCC as our chief evangelist. And any conversation I've ever had with Neil, he knows the people, he knows the company, he knows the technology. It's really, really interesting. So I encourage you after to make sure you have a great conversation with this man, because he's a wealth of knowledge and has really interesting stories and connections. But today we welcome him to the stage. He's going to be talking about navigating complexity, challenges and innovations in launching new vehicles, which is something I think we will have some entertainment as well as education here. So Neil, welcome.
Thank you, everyone. There are very known faces whom I have worked with here in the room, as well as online. But I wanted to bring a different kind of perspective. Since yesterday, we heard a lot of different technology challenges and what are the progress being made at different companies. But I'm going to talk from an OEM perspective. Before we do that, I want to thank all of you by playing a video. This is to enable, all of you have enabled us in the OEM world to make a car dance by your computational capabilities that you have instilled, as well as the software. I just wanted to show you that this was for fun in our engineering team, just to make the car dance for a change using the ADAS signals. And this shows the capability that what we could do as well for fun. That being said, my experience in the OEM, I've been in the OEM area since 2018, and I've been involved in 2 different cars from 0 to 1, which means in the startup world, started with a PowerPoint and then launching the car. And being involved in such an aggressive phase has given me a lot of different ideas, challenges, and what technology can do or cannot do. That means I want to give all of you what I've learned so far. But my experience in this whole space has been around multiple different technology domains, software, you name it, and I've been around the block in different companies. But when I went into the automotive tech again, I found out that whatever I did previously in other companies have become all applicable in the automotive world. It has converged, and that helped me. But if you look at it, since 2004, the DARPA Grand Challenge started off this autonomous, I would say, the practicality of the autonomous space. Now we are in 2024. We are really not yet there. And that has to do with a lot of different things. And I'll come to that. But if you look at the number of accidents, this is from the AVCC slides, and it's still going on. And what have we done so far in the last, say, 2004 till now, right? But if you look at the overall adoption of the technology space, the adoption life cycle, autonomy, or I would say in the OEM world, or say automotive world, we have been the slowest. And others have leapfrogged all over the place. But our world is complex. And from a technologist view, if you see the SAE levels, obviously it has been defined. It's all good in paper, amazing. Everybody started in the beginning, I'm level 1, I'm level 2, I'm level 3. But Now, as we evolve into a different world, it has totally started to change. Because more autonomy is more complexity and more risk. And we cannot, as a OEM, launch a car that causes one accident. Because at the end of the day, if I'm signing off a piece of paper to launch a car, if there's an accident, I cannot sleep at home. So it's also my personal responsibility. Now, translating into applied technology, that's what I say. On paper, everything looks good. Amazing features and functionality. But let's talk about what are the different aspects of this. It covers sensors, it covers compute power, it covers software. Level 1, we know, okay, that's the basic level. But as we keep on moving up the autonomy stack, I would say, you see these red bullets here? The red ones are the redundancy systems, which means that as you keep on going up the autonomy, you have to keep on adding redundancy. And that's not only about the ADAS ECU only. Redundancy in steering, redundancy in braking, redundancy in power management as well. Which means that nobody could really quite grasp the kind of depth of complexity that goes behind it. That being said, what is going on here? OEMs are really under pressure. When they launch a car, customers, do they like it or not? Are they willing to pay extra for certain features or not? We publicize so much stuff. And then the customer goes, I don't want, I'm going from point A to point B. I don't need all this stuff. I don't want to pay. So that being said, all the work that has been done in launching the car, at the end, if the customer adoption is very slow, the whole purpose of the business model goes back. Now comes the other things, the whole aspect of the OEM, the customers, the tier 2, tier 1 system integrators, they're all playing a bigger role in this interconnected model, as somebody mentioned yesterday as well. But if you look at the overall average price, selling price that the customers really want to pay through all the service done in 2024, look, the average price for new cars, 47K max that the customers are willing to pay on an average. And then electric vehicles, if you look at it, that's another story. It went to the spike after COVID or around COVID, big spike, and now we see a big dip or I would say plateau, right? That gives a picture, and you see all the news nowadays, and it's all true. Now let's talk about the bomb side of things. Everything that I heard, every new ideas that I see, every tools that I see, is really good, amazing. Now comes the real part of it. What does it really cost to the OEM at the end of the day per vehicle? I took a calculation. This is basically based on my 2 OEM experience, based on different discussions with lots of companies. On an average, level 1, the basic one, 200 to 2000, depending on what kind of feature sets you're adding. Also, the software cost is segmented out here. Now, as we go up, we keep on going up the stack, and it's really getting high. And the more amazing features we launch, the more failures that we are having as well because of the complexity. And the amount of cost that the OEM has to pay. The customer is willing to pay that much? No. That's the cost to the OEM. And it's a wild, wild west out there. How much will the customer pay? Now, that's the reason when we are talking about level 2, OEMs are trying to differentiate with the aspect of level 2 plus, 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 plus. I can keep on adding pluses out there. And that's the challenge. because that's almost like a sweet spot of the dollar value that the customer is willing to pay. The higher we go, level 3 onwards, elephant is in the room now. There's 1 or 2 high-end vehicles that has conditional level 3, that's what they're calling. And what we say, I don't know, level 3 minus, that would be the way to go. But now you see the real challenge on the whole market dynamics side. What I always say is the engineer's dilemma, right? We, the engineers in the room, really come up with great ideas, really excited. But many of you guys get frustrated because you don't see anything going to the customer. There's a reason behind it. And this is one of the biggest reasons. Now, how do the brands distinguish themselves, right? There are different categories that is used at the beginning when you start off with a program to create a program. And there, I'm just sharing one of the areas. This is for design only. But if you look at it, intuitive and seamless, functional, innovative, luxury and sophisticated, okay? Luxury and sophisticated, you can always say you can do high-end software, make it amazing, everything connected. Or you can distinguish functional, you can make it seamless as well with the functions. So those are the different categories, and these are the different scores that we keep on giving to look at the sellability of the whole car. Then comes the vehicle engineering side. Vehicle engineering side is the whole aspect of putting the vehicle together. It's not only about the EE or software, but everything else as well. So that being said, there's always a different kind of score rating that goes behind in the decision-making process. These are some of the background work that many of you may not see when the OEM comes with some kind of RFI, RFQ, there's a whole bunch of work that goes behind it. Yeah. Now comes, I'm just giving an example of what does it mean? Say I'm the VP for Advanced EE and ADAS. I was asked to give RFI, and then I have to create subcategories for every feature. What are my performance targets that I have to give to our supplier or partners so that we can achieve those? There's a whole lot. I just gave an example of this without any value because those values keeps on changing depending on different vehicle dynamics, different other systems. But these are, and then how do you come up with those values? Experience one, aspect of knowing the overall vehicle EE architecture, the systems, vehicle handling, everything else, body, the size of the vehicle, dimensions, everything goes behind it. Then the big one here, homologation and certification. Everybody said, oh, we have to homologate. But do you guys even saw what goes behind it? There are 1,406 separate certifications that has to be achieved to launch a car. Right? Separate. And that means there are so many. FUSA is one part of it. We just heard about FUSA, but this is only one small part of it. And now, the funny part, these are my own experience, being in the field, being in the boonies, as they say, going through the whole homologation process. Without that, we couldn't have launched the car. So if you look at one of the pictures here, this is what the certification authorities are doing. They are getting the green one is what they say, okay, we have achieved the target. Red ones are the failures. The total calculator score comes in with the ground truth information. They're recording with their own camera, everything, and seeing how the systems are giving the data out for. If you don't pass those, it's not worth talking about technology at this moment. Now, through my experience with the previous OEM, Purposely, I'm not mentioning any OEMs because I don't want to, say anything, but safe. What is winning in the customer's mind is always safety. We have done a full research with market feedback from different demographics. It has always come out to be the same. Safer, eyes on the road. They always feel confident that when their eyes are on the road, they feel they are in control. Nobody ever wants to play with that, except for in Silicon Valley and some other places where they want to play with like a toy. Hands off, play, take a video and post somewhere. But in reality, it's always eyes on the road. Now comes eyes on the road means that less distraction on the screens. The moment you have less distractions on the screen, the person's intuitive ability is to focus on their driving. It's safer, again, hands on the wheel. They feel confident. When they drive the car, if their hands are on the wheel, they feel confident, they're in control, they feel safer. It's like a mom holding a baby, The baby feels safer in the mom's arm. It's something like that as well. Similar concept. Then the other one is multimodal interactions. Multimodal interactions are based on a person's ability to either be confident when they're talking, or they feel that the button push is better, and soft touch, they hate it because they don't get the feedback that they're confident that what they have pressed, it is accepted. So we need to think about when we define a system, think about all the end customer, what they really are looking for. Now the other funny part is, see this picture here? This is a real picture from China. I spent considerable amount of my time in China. And if you look at some of the taxis, they have amazing number of mobiles. In the traffic stop, they are one of the mobile, they're playing some games. I think that's, getting paid for it or not, I don't know. Some they're talking, some they are using for maps. It's like, what kind of distraction is that, right? But when I was in the previous company in Byton, I came up with the whole digital strategy, and we defined that the whole integration of the apps and the app ecosystem should always be there. We are talking about SDV a lot nowadays, again, but this whole concept was already in production car in 2020. And the whole SDK was launched, and different companies were able to totally use it to develop the app for the car. Then came the whole interaction. The whole screen that you see was basically defined. That was the biggest innovation at that time. You can go Google, you can find out. And that was all through software. And it was driven by one SoC. Amount of load that was used to basically define and do the segmentation of the virtual segmentation of the cluster with QNX and hypervisor and Android working. 1/3 is all the cluster side is QNX, and the whole other side is Android, which you don't see. Nobody, a user does not need to know what operating systems we are using, as long as the apps and everything works. So that being said, that innovation was already there. It was done. But many companies don't learn from all the work that was done before. They want to reinvent the wheel. But I think at this moment, sharing is more important. That's why I feel with the AVCC, I have this opportunity to share a lot of my lessons learned along the way. Now we are talking about HPC. Amazing. Great concept. HPC is the way to go. If I talk to some semiconductors company where they want to upsell their solution with a single compute, I took Elizabeth also to show her this whole car that we used. We already integrated HPC liquid cooling in an existing whole car, additional sensors, and a lot of lessons learned. All the practical aspects. You saw that homologation list, all the certifications list. Functions and features works amazing. If you see this one, the whole system with the blade computer, we are talking about blade computer here. We are not talking about chiplets. If you ask me personally, everybody will argue, blade computer is the way to go for serviceability for car. And that's because insurance companies and many others, they define the amount of money that they want to do for the insurance based on the serviceability as well. The moment you show, you open one place, everything is there, I can replace my card and put a new one with upgrades, anything I want. They say, oh, wow, okay, I don't have to spend labor money to open the whole hood and card and go underneath and change ECUs. Something to think about as an alternative as well. But that being said, this one is not easy. Amount of power that the whole charging takes to basically make this work. If I'm able to charge every day, full charge, okay, that's good. But the power degradation of usage goes amazing fast using an HVC. Anybody can say on paper, I talk to every vendor every other day, right? Everybody has amazing things on paper. The moment we start to put it in integration, we see the factor that really contributes to the problem here. Now, I joined AVCC because I'm, so excited about the new possibilities in the future. I want to do a plugin here. I want to call out two people here, Bart from IMEC now, but we work together at Intel. I was the program director for the Athavale chip that we launched in 35 different customers. Bart was also my colleague at that time. And also Murli has joined. He was a senior VP for global operations and manufacturing at Fisker. And I asked him to join us as well. 2 years we spent to make a car work and make it launch. 2.5 years in total from PowerPoint and selling the cars. That has been a very amazing experience. And I feel that when you bring practical challenges to your ideas will become much better. And some of the things that you think is amazing, maybe you can rethink a little, right? And I think also another thing, we launched the very first digital 4D radar. I know you are working on 4D radar now as a startup. This is the very first that is already launched in the market. The idea was LiDAR is too complicated. We do 4D digital radar, and that gives a much faster and better integration with depth perception. And it's working. So I wanted to, I joined AVCC. I think this whole ecosystem building blocks, we really need to come up with some good numbers and benchmark for an OEM to use. I can create a lot of data myself as part of my RFI, RFQ process. But if I can rely on data that is industry acceptable, that helps me. And that's why I feel that being part of AVCC is much more industry-centric than some of the other technology spaces that I've been to. But I think that this really comes to the sweet spot, what AVCC is doing, and I totally agree to this. And I feel if we can work together, more and more of you can join, become part of AVCC, we can share knowledge that we are already doing with each other, and that will become a very good data point for all of the companies that you're working for. And that I don't think you can send out as an industry survey, get data, those kind of data are so, I would say, personal, based on the experience of the real people, that you will get some real data that will help you. So this is what I feel, AVCC addresses. And of course, the whole ecosystem, right, that we are part of. We need to accelerate the industry. After 20 years, we are still at a kind of a phase where we are still talking. And my personal experience of launching 2 different cars over the years since 2018 has helped me learn something, which is fun, but it's also true. I was part of the tier 2 side from with Intel before, but when I was in the OEM side, every day I hear amazing pitches from suppliers. After 1 day of hearing pitches, I know how to filter. And that's a great tool that I've learned along the way because of my practical experience. Now, in the next one that I'm going to join, I'll be able to filter even more. So, but I think this benchmark, as I said, that's why I appreciate Stephen. He's leading the benchmark effort, where I feel that the work that the teams are doing is really good. And I think it has to come with more and more benchmark and ideas that other OEMs can use as a kind of a data point that they can use as well. Okay, that's my presentation. Try to cover as much as I can, but I can make slides on each and every topic that will cover 1 hour each. I have a lot of stuff that I can share offline as well. So.
You want to take a Have any questions?
Maybe from the filter side, or if you were trying to put a vehicle together from scratch, right? Obviously, there was this already existing supply-based ecosystem. Maybe on the software side, talk a little bit about what the challenges you saw from the OEM side in terms of like what the ecosystem or what the supply base didn't have, maybe that you wish they would have had.
Yeah, so the biggest work that there are actually, when you start from scratch, there are existing suppliers that you can fall back on, or people that you worked with before to bring in quickly. Then the other part is their maturity of their product, including software. Suppose a company comes and says, we have already had in 5 different OEMs, software is really solid, and we bring it in. Then comes the integration nightmare. The whole interface definitions are on the OEM side between multiple different ECUs. The whole idea of the whole stack, what are the operating system, how does it interface with the gateway, to ECU, to other ECUs, and the braking, to steering. Everybody's software stack is siloed. But once you go into the integration phase, that's where the biggest problem is. That's the biggest effort that we need to put in. The other part is performance tuning. It's horrible when you first put up in the car, you sit in the car in the parking lot. That's it, everything doesn't work. Like, so what's a nightmare? We don't have much time. And then comes the integration effort of every ECU tuning that happens. And that's a long work. And some old business model is what is frustrating many times to me is they will say, oh, yeah, this is what you defined with the interface. That's what we delivered. If you need a thing, you need to issue a change request, and here is a 100K inverse. And that's frustrating because that old model, or I always say the mafias, right, out there, and they just catch you. And that's the most frustrating side. Why China is winning? They are able to succeed at all costs. If you are my customer, oh, I have a software job, I need to get it by tomorrow morning, I work with them. And they are going to put in 20 people overnight, and by morning you get a software job. Why they are winning? There's a reason. It all comes to not the business model, it comes to the people. That's the most important part. And I've seen that. I've seen in very big company, there's one guy who is willing to do the extra mile without even informing his manager, but giving a software job. Those are the people that makes the difference. And being in a startup, you cannot hide behind anyone. I'm the person signing off on the ADAS, right? Homologation done or not done? That's my result. If homologation fails, I'm done. And if my software goes to the market and there's, God forbid, something happens, whom I'm going to depose in front of NHTSA? I'm the guy. So the kind of liability I carry on my shoulder in part of ADAS is very big. And that I think all of you need to understand at the end part of the OEM, the amount of risk that carries. Okay.
Thanks so much. Oh, sorry.
Okay.
Someone discussed this in the workshop yesterday, right? And I think when you talk about standardizing, these performance of certain use cases, again, the challenge is that different vendors partition the problem differently. How do this is the feature set. How do I implement this? You can reuse some of the, input or sensor fusion data. Partitioning the problem, I feel, is also a big challenge, right? And that's what creates fragmentation. Do we see a need for standardizing that? Do we have feature-based requests so that we can say, okay, here's a feature, here's a list of features. I need you to go off and implement that, and how you implement it, and it will provide performance KPIs based on each feature. And then it'll become, that RFI process will become easier, and will become easier for us to create benchmarks based on each feature set. And you get
that's what I mentioned yesterday as well. We do need to come up with a kind of a feature set approach. And then give a kind of an idea based on some data, right? Of course, everybody can have the input, and that helps. Coming back to the software approach, many companies are not good software guys because the modular approach to software development is not yet there. So if I say a change is necessary, if somebody has to know somewhere which part of the code to. If there's a modular approach to software development, one change here already should give you in your unit test that any impact it has on the other model. So those things has to change. Otherwise, we can never be there.
Okay.
Thank you.
All right. Thank you.
All right, thanks so much, Neil. So next up we have Auston. I'm going to try
Payyapilly.
Payyapilly. All right, so he is joining us from Bosch, and today he'll be talking about crafting the perfect chip designed for automotive domain fusion. I'm not going to waste any more time. We'll get Auston right in. Thanks so much.
Yeah, keep this.
Just the computer.
Okay, so myself, I'm Auston Payyapilly from Bosch. Some of you might know me from some of the earlier discussions we had yesterday today. But basically, I handle product management for ADAS and cockpit ECUs. Elizabeth and Stephen are my counterparts on the ADAS software and sensors, right? I just use two words, ADAS and cockpit, but there's something coming in between. That is where I'm going to talk about the domain fusion, right? The fusion of the different domains. Maybe it's ADAS and cockpit, maybe it's ADAS, cockpit, and gateway, right? Whatever you want to call it. I'll start with an analogy. I was not prepared with this speech in this way. I come from a technical background. I go very deep into topics, but being a general audience, I'll start with an analogy, right? Humans, right? Humans are a big system. You think of many things in parallel. We have a lot of domain fusions happening in our body, right? Our brain is a central computer. We speak, so that's speech. And then we smell, we eat, and we even process things on the road. Our eyes are like cameras. Our sensors are tongues, right? You have tongues, nose, smell, ear. All these are the ones you use as when you do everything on the road, whether on the road, whether you're at your home, right? You do use all of these, and then you drive. And then let's take this example when you're driving on the road. You see, with your cameras, which is your eyes, but then you also feel the road to make sure that, okay, am I going faster than I should be? I mean, sometimes you watch the speed signs, but at the same time, based on the road curvatures, you know if your the wheel speed is more higher, right? So you have an experience there, and the brain is processing. Now, while you're doing that, you have some thoughts in your back of the mind, or you are listening to a song, or you are listening to the navigation, right? That is your infotainment part. I mean, I talked about ADAS, where you are driving, you are the brain and the sensors, but now you are bringing this value from home, right? You have your kids, or you have your memories, or you might be angry with your wife, whatever, right? All these cognitive load scenarios. But we are handling that well in most scenarios. Of course, there are certain scenarios where you are offloaded, you get distracted, but human brain is kind of a central fusion domain, right? That is where I'll start. And then as every slide these days everyone starts with this picture, like in a different form. You have seen it already 3 times. Without explaining the left side, we are somewhere in the domain centralized world, fine. We are going to be almost there at the centralization. Centralization can come in many forms. You can have one big ECU with multiple rack and blade, as Neil mentioned, or can be a single chip, or even few ECUs connected to each other. I mean, it needs to be central somewhere so that it can have access to internet, maybe directly, indirectly. Software update is a must, so you need a high bandwidth between the data channel where you are getting the data from the cloud to the end nodes, right? That is just centralization. Since nobody talked about the cloud native or the future, I will still bring some point there. We already started seeing the trend of having some functions offered to the cloud. You would argue that, yeah, it's not real time, you can't get everything fast enough, process it, send it back, right? But the speech recognition is a simple example, Alexa or the Google or Siri, right? While you drive on the road, you can still get that non-real time features still active with the cloud, which is what we see now. Second is maps, navigation, media, right? These are still on the cloud, you don't download anything. Another example on a daily life, if you look at any of your apps in your phone, most of the apps, except few of them, like banking, for example, the apps are completely running on the cloud. I mean, the content of the apps. The app is on your phone. The banking app might have all the things listed, only the data, the numbers of the bank, the dollars in your bank account, for example, comes from the cloud to your phone. Everything else is in the phone. But if you look at Facebook, YouTube, or all these entertainment apps, right? The app is just a placeholder or kind of a web browser, and then the information is downloaded dynamically to the phone. And then that would be a future where you see infotainment HMI or the human machine interface in the cars would be at some point. Again, you do that some functions right now, like changing of your themes dynamically with AI. That's something we see in like CES or events, right? Is where the industry is going to be. That is where the cloud native things come. But on the ADAS side, since we are talking about AVCC, the same perspective applies. Cloud is getting connected. Maybe you don't use it for everything real time, but then if you're driving to to an intersection and there are people pedestrian crossing, right? And you don't see it far ahead, but the system knows that there are people, the traffic light is changing red in 30 seconds, and your car is going to approach in 30 seconds. The cloud information must not be like real time, right? You can have few millisecond difference, but the car is getting that information. Car can slow down, whether it be saving fuel or saving electricity or the battery charge, right? But end of the day, trying to slow down well in advance to save people life, right? That's also a scenario which is something going to come in future. Coming back to the point, right? We talked about centralization, and centralization can happen in many forms. Neil was perfectly explaining the rack and blade system. We from Bosch, we have been working on rack and blade system for many years. We had it in production. I don't know, the last time when we launched for Jaguar Land Rover, which we can officially announce, it was like 9 years ago, with the Intel chip Apollo Lake back then. It was a rack and blade system, exactly like what he was mentioning. You can take out blades, but physically it was PCBs back then, because there was no investment or there was no interest from the OEM to put an extra cost on the mechanical housing so that you can take that piece and replace it. The idea was scalability back then. Like you have a car trim line needs this features, you have 4 blades, versus if you need a higher trim, you have 5th blade, right? But now we are seeing the new trend where, if you see this picture as an example, it is called like a rack and blade, but with cartridges, or you can physically replace that units individually, maybe by the dealer, maybe by the end user, right? Depending on the OEM, where the ECU is being placed. This is one of the trends we see. This is one of the ways the OEMs are currently looking at centralization. Again, fusion of domains, But if you see on the picture here, the fusion of domains really stands on different domains on different PCBs or different processors at the bare. So the domains are separated, it's safe. There is no interference between the domains. You keep literally adding all those individual ECUs to one big box. So you still save cost. I would say you still save cost from many factors, but then you have the same challenges. Like you have to design the system separately, you have to test it separately, you have to validate it separately. You save cost on part numbers in some cases, but you save wiring and so on. But now, what we are doing that in parallel, right? Some OEMs can afford to go that way. It is for the high ends or when you have money to invest in each of those on a car line, right? $20,000 car line might not be able to take that hit. Maybe a $50,000 car line can take that hit. That is where we are bringing the next solution, where we are trying to bring all those domains, maybe different domains, ADAS cockpit as an example. Here I'm also talking about body motion, gateway is another example. You can bring that all on the same chip. That is where the next trend or the next generation is going to see, where you want to save more cost. Stan was mentioning today morning, the data, if you start the design with the data and then revolve everything around it, like data is the center and not the processing, that is how the system should be designed. I agree that's how exactly the system should be designed. The pre-silicon benchmarking yesterday we were talking was also going to the point that if your software can run on that particular hardware well enough, or should you try on a different hardware, right? And then you find where it is not hitting and then optimize the system wherever. And then same way when one of my speakers was speaking about if you are not using certain cores in most of the daily operations and that particular core is getting aged, right? You can reload it in a different core. So those are the kinds of ways you can think when you use that system. But end of the day, a single chip systems save cost for them, right? You don't need too much of development, right? You don't need too much of parallel PCB components. You can save there. Beyond that, as a tier one and an OEM, right? Part numbers are going down. You don't need 10 parts and you don't need 10 project manager managing. You don't have 10 failure points. You have everything as one point. Of course, the challenges are more, but you end up in that situation where you save cost. Going back to the data model, right? Stan's point. When we revolve around creating the data, how much data you are getting, and then designing the system, you are coming from bottom to up. The OEMs are typically seeing from top down. Like, I have $25 to be invested in this particular domain. What can I get for that money? So they don't talk with data. They start with, okay, I have this much dollars. What can I do? Now you have to decide that dollars, like whether 25 or 500 for an ECU, for the sensors, for the cabling, and anything around this hardware, software development, engineering efforts, right? That is your invest. And they start from there and they look at it. And then we start from the data side, and then parallelly we come from the state of the art. Okay, you need to have this many sensors. This was one of the questions we had yesterday. What are we going to benchmark it? Are we looking at a 5-camera system, 1-camera system? Are we looking at an SAV level 2 system or a level 3, right? You need to look at all these points, and then OEMs will be like, okay, we can't think of all these. Let's go back to the cost model. We start from the pricing, we start from the cost. What can we put in, right? That is where this concept, where you put the domains to a single chip helps, right? You don't talk about the features immediately, but you start about how you do it. And then the second aspect here, like a human brain. You can use the same brain for many different functions. When you're driving, you focus on driving. When you're doing something else in your home, like whatever, or if you're going for listening to a speech, then you are focusing on that. But you don't use your brain for driving at that point, right? So reusability when not being used. And then adapting the same brain for different needs as and when needed. So it's the same brain, but you are just taking it differently. Finally there, like everyone's brain is not trained well for a different purpose. Like some people are trained to calculate faster, right? Some people might be good in doing some other mathematics or estimating something or smelling and feeling, right? So depending on what the trim level requires, we might need to train the system accordingly. Again, going back to the pre-silicon benchmarking, yeah, you need to know which all parts of the chip is being used, right? And then use that core well and find a way to utilize the rest of the cores. So starting from a system level, on a cockpit, I come from a cockpit background. My almost all my career have been in cockpit infotainment systems back then. Then we saw this transition from an infotainment system to a cockpit system where a cluster was added, right? It was a few years ago, I would say 6 years ago. 2017, 2018 time is the time when the industry was transitioning to that cockpit system. We had the same stocks, what we see now. Okay, can we put the safe domain with an unsafe domain, right? We overcome that over the years. Now you hardly see cars without having that single system doing clustering protect. It is a transition period, and we have challenges, right? There is security challenges, there is cybersecurity and few function safety challenges, and of course there are cost challenges, and technology is also growing around it. That transition is what you can think here. Along with instrument clustering and infotainment, you can also think there is entertainment, right? Racer entertainment, passive entertainment. Of course, that is part of the cockpit domain. In some cases, you also see driver monitoring as an example, or cabin monitoring as an example, also added to the same ECU. Again, depending on the OEM, you would see it differently. On the ADAS side, if you look at an ADAS ECU or the ADAS blade, it would be taken care of in some cases cabin monitoring, but then the parking scenarios, driving scenarios on level 3 and below, and level 3s and above, right? You would see that transition. And on the system level as a tier 1, when we look at what are we talking with, what is our ECU talking with? On infotainment side, you talk to different things versus on the ADAS side, you talk with different things. Let me start from the left, right? ADAS, since everyone comes from the ADAS topics at AVCC. You talk about the different sensors, camera, lidars, radars, you have ultrasonics, and you have typically any of the control buttons or CAN messages to talk with the other issues like steering, braking, right? Infotainment is way complex in that sense with the interfaces. And infotainment is not that safe compared to ADAS, but the interfaces, the interoperability challenges, what we face from infotainment is much different. You see here there's like not many smaller boxes on the interface side. You talk with the radio stations. You have the same ECU talking with 100 radio stations in a day, probably, if you're driving around far, right? The same ECU might be talking to many different stations or FM, AM, SXM. You have tons of phones with tons of different Bluetooth, Wi-Fi chips in it. You talk with, even though smartphone have CarPlay, Android Auto, you still have iPhone 7 to 12 or whatever you use, right? Interoperability is a challenge we face on a daily basis. Then you have the audio, which is not regular for an ADAS system, but cockpit have all these audio channels, whether it be speaker input, speaker output, or microphone input, and if you have any amplifier in the system, all those are interfaces we do. So coming from the chip view, if you look closely, we have more of interfaces required for a cockpit system than an ADAS system. But then we come from on a cockpit side on a lesser safety and more security, and the ADAS systems need to be more safe and then have less chance of being attacked, right? So the attack vectors are less. And of course, the camera to the infotainment system is there. You see a reverse camera, for example, and you see some of the cabin monitoring. But then overall, the interfaces required for a chip on an ADAS side is less on number of interfaces, but the compute in terms of the AI capability required for an ADAS is much higher. For a second, I'll just switch here, and then maybe I'll ask a question to the audience. It was one of the questions yesterday in Steven's poll. How many tops do you think you would need for an L2 system? Can anyone tell me a number? Right. If I ask the same question 5 years ago in the same room with the same people, your answer would be maybe 1 by 10th of the same number. If I ask the same question 10 years from now, you would have 10 times the same number. There is no end to it. I mean, it's like humans becoming greedy, right? You need more, you need more. And why you need more is, again, it's not just the interface here, it's all the data coming in, the same data Stan was mentioning. Yeah, you have a lot of data. Every year the data is going higher. And you have cameras, which was 1.2, 1.3, and then became 2, and 2 became 5, 5 became 8, and now we are talking about 24, right? And then you have one camera system for state of the art last year versus now you'll have 7 camera system, 9 camera system. So data is increasing, which means you need a strong interface between the chip to the camera. Now comes all these other interfaces. Let's start with the camera, for example, which is here. You have a camera destabilizer on your PCB. You have without naming the companies, you have few different types of protocols where the camera data is being streamed from the camera through a cable long enough. And then you don't use straight LVDS because you don't transfer in short range. You have a serializer, deserializer combination, and then it gets to the SoC. You are talking about few milliseconds per second. And then the data there between the camera or even the display is not in MBs. The typical 4K displays, or when you look at a 7K display, whatever is seen here, you're talking about GBs per second of data. And then that data need to be real time, because if you're missing a byte in it, the whole picture is obsolete, right? you don't get anything. And that is where a strong chain and a strong data path from the whole camera to camera stabilizer and then the stabilizer getting the SoC. Now you add the complexity. You need 4 cameras or 8 cameras or 16 cameras. The typical chip supports these days 16 or 4x4 lanes, so you get 16 easily with a quad stabilizer. But then you cannot get all with the extreme high resolution. You have limitations on the chip to take care of some of them. Maybe you take care of the front 8 megapixel and the rear 8 megapixel, but doesn't do the surround view, right? You have some limitation on the chip. Again, this doesn't affect the fusion systems directly, but it affects the trim level, what you want to pitch your systems. Like if you want an entry trim, you don't take care of like all those cameras, but if you're on an L3 system or a premium trim, right, you might end up in a SoC, which is much more powerful. So coming back and specifically on the center of each of these SoC. So this picture basically talks about all these ECUs, all the PCB level components you have on the cockpit side, and then you have the same similar view on the ADAS side. There are some common components here. Looking at this fusion angle, right? How do you, what are the similarities on the chip level on an ADAS ECU versus a cockpit ECU, and then when you make a fusion chip? You would still need to have the same level of interfaces what you do on a cockpit. You need a USB, you need all these app authentication based chips on the PCB, right? So you need typically the I2C, I2S for audio. You need displays and cameras. So you will have DSIs, TPs, EDPs, and CSIs, and so on. UART for GPS. You get to use all these things there. And on the other side, you will have the camera stabilizer. So like I mentioned, CSIs are important. The radars, LiDARs might be coming from Ethernet or CAN in case of radar, right? You need a CAN interface on the chip level. Maybe it's through the microcontroller, maybe it's directly, you still need the same interfaces. What is commonly used is the memory, like the RAM, UFS storage, right? This is anyways applicable for both the SoCs. If you do it on one PCB or one box or 2 SoC, you'll end up using the same. But on a fusion system, like if you see here, there is a lot of data transfer otherwise happening. Like you get a camera image, you process it on an ADAS ECU, you get the radar information, you need to show it to the end user somehow. This happens typically on the cockpit side, right? And then there is a huge data chain between the cockpit and ADAS ECU. Starting from a plain ROS camera or a surround view system or an automated parking system, you are showing the visualization to the end user with a different ECU. When you combine all these 2 domains, right, you don't have this data chain in between. You are literally talking the same system. But at the end of the day, you don't need to put two PMICs, like you don't need multiple power ICs, multiple connectors, multiple cables to have 2 systems. So you save cost. That being the main idea for a whole fusion system. So let me stop there on the chip level interface. I have basically highlighted a few things here to show the difference. The displays interfaces, the sound interfaces, I2S or TDMs, and then without going technical, UART is normally used in ADAS also, but at least GPS normally works on UART. This is just on the interface point. And then simple view for fusion system. Yeah, you put everything in a single box, and yeah, it's fine, right? Without going into details there. Structurally, technically, fine. I'd keep it that way. And then you combine all these domains on a single box, and you see that picture on the right. Maybe some of you might have already seen this picture from our announcements last year. We have been working on this single SoC-based system for almost like 19 to 20 months, I would say. And then we even had our first hardware available early last year. We were the first one in announcing that we have been working on this technology before CES last year, and then we had our demonstration. Again, that was a demonstration last year, and now we are more progressing as a platform, right? It is not just a POC. We need to now make it happen. So we are working on the platform itself now. We are talking with various OEMs. Of course, there are challenges with the single SoC fusion. You don't get all the benefits with the distributed system, but then you also have some other benefits like cost and reduced effort from other sides. So differences in opinion, but end of the day, we have both this rack and brain system and also this fusion system in-house being developed, again with different combination of SoC. My favorite slide here, also having some numbers. How much time I have remaining?
5 minutes.
Okay. This was my interesting slide. Simple view on the left, I'll make it fast. This is how a typical SoC would be looking like on a cockpit side. A stands for application cores or APUs, G for GPU, N for neural processing or DSP, digital signal processor. ISP, crypto cores, memory, real-time cores. On the ADAS side, you find a similar thing, but the main difference I want to highlight is the GPU is higher in case of cockpit versus you would need a higher NPU, the AI cores for ADAS, right? And then you have all your DSPs for audio in case of ADAS, not relevant, but the DSP for radar processing could be something useful in case of ADAS. And then real time needs to be much more on ADAS. On the center side, if you look at the numbers, again, visually some numbers. The cockpit system, as of now, what we see a trend is like anything from 50 tops to 400 tops, depending on the OEM level and the premium segment. You see these different numbers. Demons. And then NPU, we talk about few, right? We don't know what we use the NPU for on a cockpit side. Of course, we can use it for LLMs. We can use it for personalization. You can use it for driver monitoring. But we still don't see much from the cockpit side. But at the same time, on the ADAS, if you look at I asked this question earlier, right? How many tops do you need? This goes back to these indirect numbers. The existing L3 systems on the road doesn't use 100 tops. And when you look at next year's L3 systems, you will talk about 500,000 tops. Does anyone know the number of tops a Tesla system have? No, okay, I'll give some examples if you don't. So Tesla has this hardware 3, all these numbers are public. If you Google search, you'll find it. Nothing. Hardware 2 was NVIDIA based 2 NVIDIAs, and hardware 3 is the first Tesla based SSD. They were running at 25 tops each, so 50 tops in total. That was the first FSD hardware, which you will see in all the cars around 2018 to 2021, 2022. Versus hardware 4 is now 72 plus 72, so 144, which is what you get now. If you see the numbers here, it's still nowhere close, and it's FSD. The next gen hardware 5 is at 245, so that's like almost 500 tops for the system. I want to tell that story just because the same expectation of the same term FSD or same term SAE level 3 would be different in the previous generation versus now, right? Hardware is there. It is not scalable. Like once the car is on the road, you don't really upgrade. Of course, rack and plate system you can upgrade, but software is the one going to define SDV. In the end, if without a strong hardware, without a well-designed system in the sense of chip and also the ECU, you cannot achieve SDV. And this goes back to the number, like whether it be Tesla or GM or whomever, their previous generation they didn't support, and then they have 5-6 generation to support, and then 5-6 trim line. If you multiply all these for an OEM like GM, they would have like 200 combinations. Versus they start OEM like without naming you, right? You have few car lines in Fisker, and then if you multiply the ADAS trim level, it would be like 5-10. Versus a GM or a Volkswagen would have few hundred combinations, and SDV makes it even more complex. Consider the macro plan just to close there. For designing the ideal SoC for Fusion, you will need to consider a few things like scalability is a big aspect, which is required as an OEM to start from an entry trim to the premium trim. That needs to be part of the design. Redundancy was an important factor mentioned on all ADAS systems. Do you want chip level redundancy, or do you want core level redundancy, or do you want interface level redundancy? Some of them are valuable, some of them are overhead, but when you design the system right, you know what your software is going to use, and then to use the redundancy accordingly. So all this pre-silicon benchmarking would help us to understand where our particular software would be hitting, and then have that redundancy on that part, and versus some other cores or some other computer system where there's no redundancy, you don't need it, right? You don't need to keep it. Finally, heat. AI cores are directly meant to heat. It is not separate, and then that heat is going to be a challenge for an OEM. As an ICE vehicle OEM is much challenging. They don't have liquid cooling. For a battery vehicle, probably not. Yes, it's you generate heat, you take your battery to cool it, and the same engine or the same processor is taking heat power to make that heat. So waste in both ways. The numbers are high. We started seeing ECUs with few hundred watts, whereas last generation we were talking about 35 watts is highest, or 50 watts is highest. We are talking about 1,000 watts now in the next generation of ECUs racking plate system. Freedom from interference is the main thing we talk in Fusion. How do you make sure your two of the domains or multiple of the domains don't interfere with other actors? Whether you keep domain separation model, or whether you do a hypervisor or a container or a mix of all these, you still have to design that in the chip level. Like, how do you make sure the domains get enough CPU, GPU, whatever, but also the memory bandwidth? You are using the same bus. How do you make sure that your GPU is being shared for compute on the ADAS and also visualization of the cockpit, right? So you have limitation sets that need to be handled well. And finally, as an OEM, how do you make sure the total cost of ownership in the end is handled well? You do a chiplet design, or you do a chip design, or a monolithic approach. End of the day, it needs to be handled well so that the OEM can think they have a series of chip they can buy from one supplier or the design house, or design in-house to scale up and down. Function safety, cybersecurity, I won't go deep, but these are concerns, these are challenges we also face, and then we see that we need to make that design proper from start. This is something we have been working this year to create from the demo mode from last year to really have a platform looking into all the aspects of FFI, freedom from interference, and a successful encrypted system, or whatever you call for cybersecurity term, right? Safe and secure for the end user. My last slide. You will see the trend of all the OEMs in going for different trims, different technologies, the scaling up on STB, everything will be different phase. You don't see everyone like ramping up on day one. It's a hype curve, it starts slowly. STB will start eventually, and then also at some point, maybe 10 years down the line, we would be in the same room talking about, okay, now how do you maintain this many combination of hardware software? How do you make sure our software running on the previous generation is still active and safe? How do you make sure that the chip aging is affecting, and then how do you recover from that? All those would be things we will be seeing. But meanwhile, the challenges what we have to face, or what we have to solve out right now, is the safety, security, and the redundancy challenges along with FFI. But as a team here, like I would say, we all working together for the same goal. Maybe the organizations are different, but at the end of the day, we all are looking towards a brighter future. Yeah, with that, thank you everyone. I'll be open for questions.
I think we can take one quick question.
Okay.
There are no quick questions.
Oh, there are.
Could you go back one slide?
Yep.
You know, your first bullet point there on the right is scalability. Can you talk about scalability of a Fusion SoC in terms of the compute engines, and then bring that to like memory bandwidth needs, how you scale that?
So when OEM point, scalability basically means the trim levels, right? From a car line point, it's not the trim lines, mid trim levels, basically low, mid, high. And it could be the same car line. Let me take an example. Traverse, as an example, Chevy Traverse. It can have an entry trim versus a high trim. So it's the same car. If you want to pay 45,000 or 50,000 versus 70,000, you cannot put the same ECU. Of course you can. But then if you're putting a 70,000 cars equivalent ECU on a $35,000 car, the OEM is taking a hit. But if you're doing the other way, the end user is taking a hit. So that is where the scalability comes into. On a single SoC Fusion, the benefit of scalability is you can scale the different features on the different level. Like, let me give an example. A particular OEM, here let's give an example of Ford, who is selling ADAS or cockpit systems in Europe. And then the NCAP regulations are much stronger there, right? You need more safety features there. You can use the same system, same Fusion system, having the same ADAS features required for the region, but because you are using more of that compute, whether it be AI or CPU, you cannot do much with the infotainment side. So use the same ECU, but then you put more focus on infotainment, sorry, cockpit. And then when you
partitioning of
yeah, and then you dynamically can adjust the software now, right? Now coming back to CPU cores, and ideally, if I was supposed to design a system having Fusion, you would try to do partitioning in terms of hardware. First of all, software can partition. You can keep things separately in software. But if you have enough cores to separate, keep it separate. And if you are okay in adjusting, taking the hit of the cost, right? You have 2 GPUs and you have multiple cores, clusters of CPU, multiple NPUs. You can even divide some of these functions for one for ADAS, one for cockpit, and then even dedicate memory bandwidth for those. Even of course, you can even put 2 memory modules and even have separate lanes for it, right? You can design that way. Then it becomes a little bit costly, overhead is higher. But then if you want to keep it on the lower trims, maybe you don't give that flexibility. And then you don't tell that your system is an L3 at that point. You can do an L2, L2 plus system with this same Fusion methodology. Versus if you want a high-end L3 system, but same Fusion, you might need to design it differently. The bandwidth numbers anyways doesn't really matter, but it goes back to how much data you are getting, right? If you have too many cameras with megapixels, I don't know if you know, the human eye is 576 megapixels. That is the number we hear. 576 is not a number you see in any car, right? You have what, 12 megapixel, two of them, and then 8 few of them, right? You're talking about 50 versus our eyes are 576. In 10 years, we'll be looking at those big numbers. And then our bandwidth on the chip level is going to be the bottleneck unless we design it right now.
Thank you so much.
All right, I know we're smelling lunch that's being wheeled into the room right now. Can't wait to introduce you back to that. But our final speaker of the morning sessions, I'm happy to welcome Bart Plackle to the stage. He is the Vice President Automotive at IMEC and is in town for an IMEC chiplet discussion conference. And he's going to be talking about the challenges in land of automotive high performance computing chiplets to the rescue. So Bart, thank you for joining us.
Thank you, and it seems that I'm the only one between my presentation and lunch, so not always a good spot to be in, but hey, let me start off with a quick raise of hands. Who knows IMEC? Oh, I actually more than I thought. Okay. So we are probably the largest non-for-profit or R&D organization in semiconductors. We've been building the roadmap of transistors over the last 40 years. The reason why I'm now here and why we also have the event in Michigan the next day is because we are now trying to do the same for automotive as what you've done for semiconductor. Is there a clicker or should I adjust the output?
Nope.
Just maybe. Okay. So in next 20-25 minutes, I'm going to walk you through why we believe that chiplets is going to be a solution in the future. Why we are seeing that the classical way of always putting more and more transistors into an architecture that's bound to fail, and it's just physics. We're also going to quickly address like how other market segments, automotive on a few fronts is a little bit slow, but other markets already transitioning to chiplets, and there are some quite good learnings on how that's happening. And then the last part of my picture, what I will discuss is what is specifically IMEC doing in this transition from monolithic-based architecture. So it was a lot of sanity check with the previous presentations, how we're going to consolidate more and more. And by that consolidation, we're seeing that we have to have much more performance. And sadly enough, when we need the performance the most, which is now we're scaling into the levels of autonomy, we're scaling and bringing the large language models into the car. That's exactly the point that the classical Moore's law is failing. So we need to have other recipes. We're not saying that we are not going to scale in Moore's law. We're just saying that by far it's not going to be enough. Before diving into the chiplet itself, quick introduction from IMEC. So I'm responsible for the automotive side, and I have two sub-sectors of business units. One is sensing. So everything that we're doing within my sector is two things: making sure that the car can see more, and making sure that we have the processing power that we can handle all these new sensors. So on the see more, we're doing a lot of technology research on multispectral. So this is where we have quantum dot-based cameras. And next to the visual spectrum, we can really cherry pick which spectrum, which wavelength bands we want to monitor. And depending on which bands you select, you can see better eyes, you can see dark tires on the road, etc. So there's a lot of research happening with this multispectral cameras. Radar was also mentioned in I think two speeches ago. So we are working on the next generation radar. Definitely want to catch up. But for gigahertz radars, coherent radars where we have multiple front ends which we align with each other. And we're also building on silicon photonics based LiDAR. So true state solid state architecture that allows you to see 300 meters out with a very good angular resolution. So that's what we're doing for the sensing side. And then, of course, if you have all these sensors, it was mentioned here a few times again, new sensors, more capabilities, more bandwidth. So you need to have much more performance. I do think that if you build out the ideal car today already, you can already create pretty much a very good environment, the perception of what is happening around your car. I think where we dramatically fail is trying to predict how the scene around us is evolving. So we as humans are very good not only understanding the landscape around us, but we can also project and try to think ahead on how a ball on the street is probably going to be an issue with a kid playing there. So those perceptions and predictions need to come as well in the architecture. So more sensors, more capabilities, more horsepower we need. And then at the same time, this is just for the ADAS, for the autonomous side, for the cockpit side. We see now large language models coming into the car. Again, that gives us a rise in performance capabilities. And this is where, as I said before, this is where we see it breaking. This is where you cannot start raising your die size. We are getting to a point that you're getting into a reticle, so pretty much that you use all the die real estate, and then still we see we're not having enough performance. On IMEC, and this is a slide. So this was, I'm not sure if you recognize this. This is Dr. Mee. He is the COO of TSMC. ITF World is our flagship event. We have typically 4,000 people coming to Leuven. And this was a very nice explanation from the doctor outlining what impact that IMEC is doing purely for the processor side, right? For the CMOS side. So typically what we are doing is we are researching next generation transistors, whether it's high K, we did that already 20 years ago. Now EUV, very popular in our sheets, back power side delivery, CFETs, and high NA. And typically, if you see when we start evaluating and building these, because we have a 300 millimeter fab in Leuven, we are now also building a 2 nanometer pilot line together with ASML. So we have infrastructure to build all these structures. And typically what you see is we're like 5 to 10 years ahead of the market. That's what we do for core CMOS. And that's not what we want to do for the high performance compute, where we lay the groundworks on how this will evolve over time. And hopefully in 5 or 10 years from now, I can show a similar drawing like, hey, this is what we did in 2020, and this is now the adoption of the overall architecture. So this is the most fundamental slide, I think. Was already discussed by a few. If we look at the volume of the cars, it's not going to increase, if everything is going to decline. And with the decline, we have a real issue because our volume of the cars and SOP cars is like an order of magnitude lower than cell phones. If we now see the technology, and that's very like the previous presentation, the technology demands of the perception platform, the high performance platform, it's exponentially increasing, and it's far beyond what a cell phone platform is capable to deliver. And then, of course, you have a big issue because we now have to bring technology in a very aggressive timeline, divided by 80, 90 million, and that assumes that all these platforms are going to use, so in reality maybe 10 or 20. So low volume, extreme high performance requirements, and to hit those performance requirements, you have to go to the latest and greatest process nodes, and you're developing or you're building systems that now cost in the range of 1 billion. So 5 minutes looking at this diagram, you know that the business case is absolutely broken. You can no longer build like a platform which is like 10, 20, 40 times faster than a cell phone, half the market, and then just become cost competitive. So we have to do things differently. We cannot go in a normal way with the exponential growth of the performance of the requirements. A very wise man 6 decades ago, he said like, hey, as long as we can reduce the feature size of a transistor, we will be able to have double the performance every 18 months later again, 2 years. And that's what's propelled actually the semiconductor industry for the last 4 or 5 decades. It worked well. Whenever you had an architecture at Intel, and Neil probably still remembers this, sometimes you didn't get clear market requirements, and then you say, okay, the next platform is going to be 10-20% faster, and you get it pretty much for free by going from one node to the other. A lot of times, that was not how the next generation product was built. At the same time, that's the interesting part. When you go lower and lower in your feature size, in the transistor side, we are getting now in angstrom era, where we're building transistors on a few atom layers. And then the classical electrical laws don't apply anymore. It becomes voodoo or quantum, no matter how you want to call it. And this really is not good for scale. It's becoming so hard to keep on this 18-month or 2 years doubling of transistors. That's no longer going to work. And because he made that claim, he was the one actually predicting that this time was coming, and we believe it's now coming. And he said it may prove out to be more economical building large systems, smaller functions with separately packaged in the connect. That's exactly what chiplets are. But that was a long-term vision that he outspoke just based on physics, and we're now getting there. So in a nutshell, what does it mean? My CEO would kill me if they say we're no longer going to do research on the transistor side. So we are full stream ahead on getting the next angstrom type of transistors. So we're building nanosheets, CFETs, 2D FETs. So we're still building that. As I said, it's going too complex. We need to have way different means of applying power, doing clock network, etc. We're still doing it, but the efficiency gains are not there. And to really build very high performance platforms, we have to combine this with very smart 2D, 2.5D, 3D packaging. So this is our 40-year history or legacy, and we've been dealing now with 20 years of 2D, 2.5D packaging. And this is really where it's now coming together, and we believe that this is the right technology for building the next generation high-performance compute platforms. So are we the only one thinking like, does it really have to be a chiplet, and why is it commercially viable to build it in chiplets? Can it sustain reliability? Well, just look at other markets. And the first one, that's the last design when I was at Intel where I was working on the vacuum. I mean, that had so much processing, that was exascale on a single package. I mean, it was very obvious. There's no other way if you want to have so many transistors on a substrate, you have to split up. All these things are way beyond radical, so you physically cannot build it otherwise. But then if you are going to split it up into multiple processors, then clearly you have to connect them, and you have to connect them with a very high bandwidth, because otherwise the architecture doesn't work anymore. You have to make sure that they have also very high connections with the memory, otherwise the architecture doesn't work anymore. So that's the reason why you start disaggregating, and before you know it, you end up with 47 chiplets. But that's the highest end that we've been working on. Then, if you go down from the exascale to just server, you'll already see other products which already, for the same reason, they disaggregated. So actually, everything that you see here, those are 3 chiplets, 3 chiplets, 3 chiplets, 3 chiplets, and an integration die. And for them, it's where we've done the calculation. And if you would build this in a single monolith, then you're so close to the radical that you lose enormous amount of yield. By splitting or disaggregating the architecture here, they were able to save anywhere from 15 to 20% on the cost by yield recovery. Because if you have a yield defect somewhere, in the worst case, you have to throw a very small thing here away. You have one big monolith, you have to throw the whole monolith away. So very good economical rationale why to do this. So exascale, gone chiplets, data center, have chiplets. And now what we see here is even consumer side is moving into chiplets. Look at Intel Meteor Lake. So they have disaggregated in different functions. So you have CPU, you have an I/O, you have an AI accelerator, and this really allows them to mix and match different capabilities, so different performance levels, but also all these things can be implemented in different process nodes. So you can really optimize your I/O doesn't scale, so why would you implement this in 3 nanometer? For a neural network engine, that's probably you want to have so much logic density for your computation. You want to have it in the smallest process node. And then CPU, you can have it in between. So consumer product, and also even the Apple M1 Ultra, it's really a homogeneous chiplet, it's built to build. So you build one, make sure you have a very high performance standard interface. And if you want to scale up to the next level, to the double of performance, you just interconnect them and you make sure that the infrastructure is there. So that's what a high performance compute market is doing today. So that is only one question. And the only one question I have for you is like, do we believe that autonomous vehicle 2030, an autonomous vehicle with a good in-cabin experience, do we believe that at least it will be in this type of performance league? And if it is in this type of performance leagues for 2030, then why wouldn't we have to go shipless when they have to go shipless? From our point of view, it's very clear. We have to, if you want to have similar type of performance, we better go into a chiplet. And that's not right now, just like opening a can of worms, because this works in a very controlled environment. If you try to have this work in the automotive physical conditions, so the SQ grade 2 or 1, at the automotive vibration, it will fail dramatically. So what we are now trying to do is like reuse this infrastructure, reuse the knowledge of chiplets, but making sure it's going to survive in automotive. For those who know the Automotive Congress in electronics, it's one of the highly prestigious conferences in Europe. And this is where we asked the audience, actually the moderator asked, like after we've done our talk, we asked like, how do you see the importance of automotive chiplets? And this was the only poll where you had like 0, no use for chiplets in automotive. So the outcome of this, I think it was like 400 execs from the automotive industry, was anywhere between extremely important, 30%, very important, 43%, and may become important, 23%. So the market is trying to understand we have to go there. Trying to speed up a little bit. That's too fast. So what are we doing? So this is a kind of classical, this was my Intel job, right? We were doing very high complicated monolithic architecture. All the building blocks were in the same real estate. And now we're really disaggregating. We're looking for what are the building blocks that make sense to operate independent of each other, that can have a different roadmap. So you have an accelerator, for more main CPU, you have some I/O, you have a GPU. So once you have to disaggregate it because you're not going to get performance, a totally new, very bright world opens up. First, performance and power scaling. So you can now, here you only have one processor. So whatever you choose here, all these IP building blocks are going to be on the same processor. That's by design. This design, you can match and mix and match the right processors to the right chiplets. So you're going to have a high performance, lower power product. Composable, that's the example that we use for Intel. So you can make like 10 different products, and those 10 different products, you create different SKUs by sometimes changing the CPU, sometimes changing the GPU, sometimes changing the I/O. So just by adding or removing some of the chiplets, you create a totally new package. And then rather than doing full tape outs, which costs you an arm and a leg, you can just do it by assembling the right number of SKUs. Yes, you still have to do the tape out of the individual platforms. Yield, I think we discussed, if you build this and you have the Poisson distribution and you have a few errors here, you have to throw it away all the time, 100% yield loss. If you have the same yield distribution, yeah, sometimes you have to throw one of these away and you replace it. So it's going to be more cost effective. Scaling, we heard a lot about scaling. It allows you, depending on if you do the right architecture, it allows you to say like, hey, in my low-end constellation, I'm going to only use the base CPU chiplet die and then maybe small accelerator. And as I'm going to grow, I can build a bridge and then I can put more memory, I can put more accelerators to that as well. The last one, time to market. If you do such a chiplet, You know, the most stressful time is the takeout. Everything needs to be locked and loaded. RTL is frozen. Well, in here, all these things can have a separate lifestyle. In store, you still have to have all the shiplets ready from the moment you integrate it. But after 1 year, after 2 years, where I say, hey, this product is actually very, very good. Only this part here is outdated. Then you can just say, hey, I'm going to retape out this one and leave the whole infrastructure in place. And now after 1 or 2 years, I can come up with a new product. Because seldomly, you will have to update all the IP building blocks at the same time. 5 minute wait time?
5 minutes.
5-0?
Yeah, 5. 5 minutes.
Okay. I cannot do this in 5 minutes. Okay, I'm going to just skip a few things. This one, I think you've seen a similar slide from Thomas, I believe. So we're very close collaboration with Bart, so we've probably seen this. So what are we then doing? What is IMEC doing and how are we doing acceleration? As I said, this is our school book of 3D packaging. That's 20 years of history. We have all the technology from wafer stacking, die wafer stacking, high density wafer stacking, through silicon device. So we have all these things in the cookbook. What we're now looking at is like from all these cookbooks of technologies, what will survive in automotive? What will be affordable in a 2030 timeframe? Like to go fast. So we started this crazy endeavor by just writing a white paper just 8 months ago, and throughout that journey, very quickly this became out of control. And now tomorrow we are having our first automotive shipment conference here in Ann Arbor, and it was totally overbooked. So we now have like 130 people on site. One topic, everyone, whole ecosystem together, just to discuss chiplets, automotive chiplets. We are creating an automotive chiplet program. I'm going to be very fast. So what is the automotive chiplet program? It's really proving out that the technology that has been used in the high performance market, that we can use the technology in automotive. And we have all these 6 buckets that we are collectively with all the parties are validating. So quality reliability, will it work? Architecture is like, how can we come up with an ecosystem that provides enough scale that everyone talks the same language, how it integrates, and on the political side, the scope, our scope, so you can apply chiplets in various flavors. We are very focused on the high performance compute part of it, focused on making sure for 2030 it's affordable, making sure that if you build chiplets, that they're not designed for one specific implementation, but that they can be used in different platforms, so standardization is key. And everything with the industry is pretty competitive. So we are bringing the whole ecosystem together to collectively decide where to move forward. So there's a little, so quality reliability, they go hand in hand with the architecture. The work markets are being defined. And if you can wait until tomorrow we have a very big press release here where we will announce 10 partners who are building this together with us. Some of these partners are here in the room already. So, but it's going to be a great event tomorrow. 10 parties are already committed to make this happen. Some of them you can already see here. Here we have Dipti in our key event. We have BMW here, we have Valeo here, and tomorrow you'll see 7 other ones. Few more minutes. Good. So this is everything goes extremely fast. So this is our 3 years journey. So we started 18 months ago by pulling the ecosystem together. That's what we're doing tomorrow. We now call it a STAR initiative, and the specific topic is automotive chiplets. So that's something we started March last year, rallying the ecosystem. This year is really turning all that knowledge and the guidance from the ecosystem into actionable research, as I explained, quality, reliability, and architecture. That's what we want to make sure that we are getting aligned. And then the next phase is like, how are we going to make sure that all these learnings get into an actual vehicle? And to be honest, if we would just take these learnings and we go to the OEM, it's like, hey, now we have everything, please implement it. That's not how it's going to work. That's way too much risk. It's still tons of things which are not validated. To do that, we're going to take these proceeds, we're going to build a reference platform. So we're going to physically build such a thing where we have takeouts of shiplets. This is led by IMEC. For the first time, this is going to be a program that is not going to be led by IMEC. The closer you go to the industrialization phase, the closer we want to work with industry partners. Tomorrow you'll see which these industry partners are. It is going to be based on all the learnings we have. And given the capital intensive nature, I mean, if you're going to take out 4 or 5, we're easily talking about 200 or 300 million. So that's something that we cannot do on our own. So we are looking for federal funds, local funds in Europe, local funds in the US, and also in Japan. So with that, I would like to close up. So I sorry for using a little bit more of your time. But the thing is that we started Shiplets 18 months ago. We brought the ecosystem together. We now kicked off the automotive shiplet program, and tomorrow we're going to build it out. And that building out the reference platform, that should be the golden architecture to serve in the industry, to serve the OEMs, to adopt this with very low risk, and that they have an 80% like pre-approved architecture with the software stack, etc. That's our goal for next year. Any questions? Okay, we have.
I have one. So, I mean, the alternative to chiplets would be to scale up by just making a bigger PCB and having multiple full chips interconnected. Since the car is not as space constrained as a cell phone, what would be the big win for why chiplets over PCB approach?
Yeah, actually, the answer was given by the previous talk. The more functions you have that require massive amount of bandwidth. So if you need to have a lot of interconnects between some of these components, CPU, GPU, accelerator, memory, etc., the more interface you have, the closer you have to bring those things together from a power perspective, but also making sure that you have the physical integration, that you don't have to go over long wires or GSML or what have you to interconnect them. So if you can split your architecture in a way that they are very loosely coupled and they don't need a lot of bandwidth in between, go knock yourself out and you don't need to go with chiplet architecture. If those functions have to be very closely integrated from a performance, from a bandwidth perspective, etc., I think chiplet is the only way out.
Thank you so much. Thank you, Bart. We are going to break for lunch now. We're running 15 minutes behind, so we're going to shorten lunch just a little bit. So lunch is on the right-hand side of the room. We will come back into the working group meetings. Reminder, benchmark is in here from software portability across the hall, and there will not be a cybersecurity working group meeting this afternoon. And I do have one pleasant surprise. So we have an opportunity to see a Fisker vehicle in the parking lot. We have a guest here who will be offering tours of the car and discussions. So if you're interested, could you stand up?
Yeah.
Excellent. So if you're interested, please come over and introduce yourself and explain what area you're interested in.
Yeah.
And Fisker will be meeting out in the parking lot during lunch to show the vehicle. So any questions? All right, we'll see you back at 1. Thanks much.